Hello there, and welcome to Sleepy Cosmic Lens, where curiosity gets comfortable, science takes its time, and the universe becomes a little easier to explore before drifting off for the night. What if everything you know about distance is wrong? What if the stars aren't as far away as they seem, and the space between you and the farthest galaxy is just an illusion, a trick of geometry? Tonight, we're setting out on a journey toward one of the strangest ideas modern physics has ever produced. An idea that sounds as though it belongs in a work of science fiction, and yet emerged directly from some of the most serious equations ever written. Tonight, we're talking about wormholes. We'll explore how these cosmic shortcuts emerged from Einstein's equations, why they keep collapsing as soon as they form, and the truly bizarre matter that might be needed to keep one open. We'll journey to the edge of what we know, and even beyond, into the strange territory where wormholes might not just connect different places, but different times. And finally, we'll discover how these tunnels through space might be clues to the deepest structure of reality itself, linking quantum physics to the very fabric of the cosmos. Now, the word itself is admittedly a little odd. It sounds less like a profound feature of the cosmos and more like something you might discover in an apple that's been sitting in the fruit bowl for a bit too long. Yet behind that peculiar name lies a possibility so extraordinary that it has fascinated scientists, writers, filmmakers, and dreamers for generations. Imagine stepping through a doorway and emerging somewhere unimaginably far away. Not after years of travel, not after centuries aboard a spacecraft, not after crossing impossible distances 1 kilometer at a time. Just there. One moment you're here, the next moment you're somewhere else entirely. Perhaps another star system, perhaps another galaxy, perhaps somewhere so distant that light itself would need millions of years to complete the journey. The notion feels almost magical. And yet, surprisingly, it wasn't invented by novelists. It appeared inside mathematics. That alone is enough to make wormholes worth talking about. Before we begin our gentle exploration, though, I'd love to know where in the world you're listening from tonight. Are you tucked into bed after a long day, relaxing on a sofa with a blanket nearby, listening during a late-night walk beneath streetlights? Perhaps it's morning where you are, and the day is only beginning. And what time is it right now in your little corner of the world? It's a fitting question for a discussion about shortcuts through space, because as we'll eventually discover, space and time have a habit of becoming tangled together in ways that are much stranger than most of us realize. If you find these quiet scientific journeys relaxing, interesting, or simply a pleasant way to unwind before sleep, I'd be very grateful if you gave the video a like and maybe subscribed as well. It helps this small corner of calm continue reaching curious minds around the world. Now make yourself comfortable. Settle in. Allow your thoughts to slow down a little. Because somewhere between distant stars, impossible distances, and the limits of human imagination lies the story of the wormhole. To understand why wormholes capture our attention so easily, it helps to start with a simple problem. Space is enormous. That's really the heart of it. Not merely large, not merely vast. Enormous in a way that challenges everyday understanding. Most of us are accustomed to distances measured in minutes or hours. The grocery store might be 10 minutes away. A friend's house could be half an hour away. Another city might require several hours of driving. Even a trip across a continent is something we can imagine. But the universe plays by very different rules. Consider the moon. That bright companion hanging quietly in the night sky often feels nearby. After all, we can see it almost every evening. Yet the moon sits roughly 384,000 kilometers away from Earth. If you drove a car without stopping, it would take months to get there. Already the numbers begin to feel unusual. Then we move outward to the sun. The sun is approximately 150 million kilometers away. Light, which moves faster than anything else in the known universe, requires about 8 minutes to reach us, and that is just our local star. The nearest star beyond the sun is called Proxima Centauri. It lies more than 4 light years away. A light year is the distance light travels in a year. Light, the fastest thing in existence, even moving at that incredible speed, still requires over 4 years to bridge the gap. Modern spacecraft would need tens of thousands of years. Suddenly, the universe begins to feel less like a neighborhood and more like an ocean without visible shores. Human beings have always struggled with that reality. We are explorers by nature. Whenever we encounter a boundary, we instinctively wonder what lies beyond it. Whenever we see a horizon, we feel tempted to cross it. For thousands of years, oceans seemed impossibly vast. Then ships improved, mountains blocked travel, roads appeared, continents remained separated. Eventually, aircraft connected them. Again and again throughout history, distances that once seemed impossible became manageable, and so a natural question emerges. What if there were a shortcut? What if space itself offered a faster route? What if the enormous distances between stars were not quite as absolute as they appear? At first glance, the idea sounds ridiculous. If 2 points are separated by 1,000,000 kilometers, then surely you must travel 1,000,000 kilometers. That seems obvious. Common sense tells us so. Yet common sense has a poor track record when confronted with modern physics. Physics has repeatedly revealed that reality is under no obligation to behave in ways humans find intuitive. The Earth feels stationary. It isn't. Time feels universal. It isn't. Solid objects appear solid. They're mostly empty space. Again and again, deeper investigation reveals a universe stranger than appearances suggest. Wormholes belong firmly in that tradition. What's especially fascinating is that the basic concept can be understood without advanced mathematics. Imagine an ant crawling across a sheet of paper. The ant begins at one corner. Its destination lies on the opposite side. From the ant's perspective, there is only one route: travel across the surface, step by step, millimeter by millimeter. Now imagine folding the paper. Suddenly, the two distant corners touch. The ant no longer needs to cross the entire sheet. It simply steps from one corner to the other. A journey that once seemed long becomes incredibly short. This famous analogy appears in countless explanations of wormholes because it captures the central idea beautifully. The shortcut doesn't arise because the ant moves faster. The shortcut appears because the geometry changes. Distance itself behaves differently. Of course, actual wormholes are far more complicated than folded paper. The universe isn't a sheet lying on a desk. Space isn't literally folding like a napkin. But the analogy hints at something important. Distance depends on geometry, and geometry can sometimes be surprising. What's remarkable is that physicists did not begin with the desire to invent cosmic tunnels. They weren't sitting around wondering how to build interstellar highways. Instead, wormholes emerged as a consequence of trying to understand gravity. That story begins with one of the most famous individuals in scientific history, Albert Einstein. Even people who know little about physics usually recognize the name. Wild hair, thought experiments, relativity, perhaps a photograph sticking his tongue out. Einstein transformed our understanding of reality more than a century ago. Before his work, gravity seemed fairly straightforward. Objects attracted each other, planets orbited stars, apples fell from trees. Everything behaved more or less as Isaac Newton had described. Newton's equations worked wonderfully. In many situations, they still do. But Einstein discovered something deeper. According to his theory of general relativity, gravity isn't really a force in the traditional sense. Instead, massive objects change the shape of space and time around them. This was an extraordinary revelation. Rather than imagining gravity as an invisible pull, Einstein described it as geometry. The Earth travels around the Sun because space-time itself is curved. The Moon travels around Earth because space-time is curved there as well. Matter tells space-time how to bend. Space-time tells matter how to move. It's an elegant idea, and it works astonishingly well. Predictions made by general relativity continue to pass experimental tests more than a century after its publication. But once physicists began exploring Einstein's equations, they encountered strange possibilities. Very strange possibilities. Some solutions described black holes. Others described expanding universes. Still others hinted at structures connecting distant regions of space-time. Not because anyone wanted them to exist, not because science fiction demanded them, because the mathematics allowed them. Imagine discovering a hidden room while carefully examining the blueprint of a house. You weren't looking for it. You didn't design it. Yet there it is, a doorway where none seemed possible. That was roughly the situation physicists found themselves in. The equations appeared to contain shortcuts, potential bridges, connections between distant locations. These hypothetical structures would later become known as wormholes. Interestingly, the name arrived much later. The original terminology sounded far more formal and considerably less memorable. Scientists initially referred to concepts such as Einstein-Rosen bridges, accurate perhaps, catchy, not particularly. Wormhole eventually won because it captured the essence of the idea. Imagine a worm crawling through an apple. The worm doesn't travel across the surface. It creates a tunnel through the interior. Two distant points become directly connected. The path becomes shorter. The journey becomes easier, at least for the worm. Whether the same principle could apply to the universe remained another question entirely. Even today, after decades of research, wormholes occupy a curious position in science. They are not fantasy, yet they are not confirmed reality. They emerge from legitimate mathematics, yet no one has ever observed one. They may exist, they may not. Physicists continue investigating. And that's one reason wormholes remain so captivating. Unlike many fictional ideas, they stand with one foot in imagination and one foot in genuine scientific possibility. The doorway isn't completely open, but it isn't completely closed either. That uncertainty invites curiosity. Humans are remarkably good at becoming fascinated by unanswered questions. Perhaps because unanswered questions leave room for wonder. We know what mountains are. We know what rivers are. We know what clouds are. Wormholes remain different. They exist in a category filled with possibilities rather than certainties. And whenever certainty becomes scarce, imagination tends to become active. This is why wormholes have appeared in countless stories. Films use them, novels use them, television uses them, video games use them. The idea of instantly crossing impossible distances speaks to something deeply human. We dislike barriers. We dislike waiting. Given the option between traveling across a galaxy for 1,000,000 years or stepping through a doorway, most of us know which option we choose. Though admittedly, stepping into a mysterious cosmic tunnel does sound like the sort of decision that would make a health and safety inspector extremely nervous. Still, the appeal is understandable. Imagine standing beneath the night sky. You look toward a distant star. You know it is unimaginably far away. Then imagine learning that somewhere in the universe, a hidden passage might connect your location directly to that distant point. No years of travel, no vast journeys, just a shortcut hidden within reality itself. Even if such a thing never exists, the possibility alone captures attention. Long before anyone wrote equations about space-time, long before telescopes revealed distant galaxies, and long before physicists began debating whether wormholes might exist, human beings were already dreaming about shortcuts. That may seem like an unusual place to begin a discussion about one of the strangest concepts in modern physics, but in many ways it is exactly where the story belongs. Because wormholes are not merely a scientific idea, they're also the latest expression of something deeply human, the desire to reach distant places more easily, the hope that somewhere, somehow, there might be a faster route, the suspicion that the long way around cannot possibly be the only way. If you think about it, nearly every civilization in history has shared this instinct. Imagine standing on a coastline thousands of years ago. You can see the horizon stretching endlessly ahead. Beyond it lies mystery. Perhaps another land, perhaps another people, perhaps opportunities, resources, stories, or dangers. You know something exists beyond that line because the world cannot simply stop there. Yet reaching it appears almost impossible. The distance feels overwhelming. And whenever humans encounter overwhelming distances, our minds begin searching for alternatives. Could there be a hidden passage? Could there be a safer route? Could there be a quicker way? This tendency appears so consistently throughout history that it almost seems woven into human nature. We are explorers, but we're also problem solvers. The moment we recognize a challenge, we begin imagining ways around it. Consider some of the earliest myths ever recorded. Again and again, stories feature magical doorways, hidden roads, mysterious tunnels, enchanted gates, and secret passages connecting distant places. The details vary depending on culture and geography, but the theme remains remarkably consistent. Somewhere beyond ordinary travel lies another route, a route known only to a few, a route capable of bypassing the normal rules. The ancient Greeks imagined hidden entrances to distant realms. Norse mythology spoke of pathways connecting different worlds. Various traditions across Asia described spiritual gates and sacred passages. European folklore became filled with mysterious roads that appeared only under special conditions. Even stories told around campfires often revolved around hidden routes leading somewhere unexpected. At first glance, these tales may seem unrelated to modern wormholes, yet they reveal something important. People have always been fascinated by the possibility that reality contains shortcuts. Not because shortcuts are easy, not because shortcuts are guaranteed, but because distance itself can feel unfair. Imagine living in a world where the nearest city requires weeks of travel. A mountain range stands between communities. Oceans separate continents. Every journey demands enormous effort. Under those conditions, the idea of a hidden passage becomes incredibly appealing. In some ways, science and mythology are not as different as they first appear. Both begin with questions. The methods are different, certainly. Science relies on evidence and testing. Mythology relies on storytelling and tradition, yet both emerge from the same human impulse: curiosity. We look at the world and wonder whether there might be more to it than what we immediately see. A child discovers a hidden door in a house and becomes excited. An adult learns about unexplored caves beneath a mountain and becomes intrigued. A scientist discovers a strange mathematical possibility inside Einstein's equations and starts asking questions. The scale changes, the curiosity remains. Perhaps this explains why wormholes capture public imagination so effectively. Most scientific concepts remain somewhat confined to textbooks and laboratories. Wormholes do not. People hear the idea once and immediately understand why it matters. You don't need advanced mathematics to appreciate the appeal of reaching a distant star instantly. You don't need a degree in theoretical physics to understand why a shortcut across the universe sounds useful. The attraction is almost automatic. Yet humanity's relationship with shortcuts extends far beyond stories. In practical terms, civilization itself can be viewed as a continuous effort to create them. Think about transportation. For most of history, movement was painfully slow. People traveled at walking speed. If they were fortunate, they might have access to horses, boats, or carts. Distances that seem trivial today represented major undertakings. A trip between cities could consume days. A journey between countries might require months. Crossing an ocean could take years. Communication moved no faster than transportation. If you wanted to send a message, somebody physically carried it. News traveled at the speed of a horse. Knowledge spread slowly. The world felt enormous. Then humans began creating shortcuts. Roads reduced travel time. Bridges eliminated detours. Canals connected waterways. Ships improved. Navigation advanced. Every generation sought ways to make distant places feel closer. The pattern repeated constantly. A mountain blocking travel became a tunnel. A river interrupting movement became a bridge. An ocean slowing trade became a shipping route. Whenever geography created an obstacle, human ingenuity attempted to overcome it. In many respects, civilization advances by shrinking effective distance. The physical world remains the same size. Our ability to navigate it improves. A fascinating example can be found in the history of maritime trade. Before the construction of the Suez Canal, ships traveling between Europe and Asia often had to sail around the southern tip of Africa. The route worked, but it was long, very long. When the canal opened, thousands of kilometers disappeared from many voyages. The planet had not changed. The oceans remained exactly where they were. Yet the effective distance between locations became dramatically smaller. A shortcut had been created. The same principle appears again and again throughout history. Railways shorten travel. Airplanes shorten travel further. Modern communication reduced distance even more. Today, a conversation can occur between individuals on opposite sides of Earth almost instantly. That would have seemed miraculous for most of human history. Imagine explaining video calls to someone living 500 years ago. You speak with a person thousands of kilometers away. You see their face. You hear their voice. The communication occurs nearly instantly. Many people from earlier centuries would likely classify that as magic, and honestly, from their perspective, it would be difficult to blame them. What's particularly interesting is that every major reduction in distance changes how people think. When travel becomes easier, the world feels smaller. When communication becomes faster, societies become more connected. Distance begins losing some of its power. Yet no matter how much progress occurs, certain distances remain stubborn. The greatest of these are cosmic distances. Even after centuries of technological advancement, the stars remain astonishingly far away. This creates an unusual situation. Human beings have become accustomed to overcoming obstacles. Mountain in the way? Build a tunnel. River in the way? Build a bridge. Ocean in the way? Build a ship. Need to communicate globally? Build satellites. Again and again, barriers fall. Then we look toward the stars and encounter a challenge unlike any before. The distances are so large that ordinary solutions seem inadequate. A bridge to another continent is one thing. A bridge to another solar system is something else entirely. This is where the dream of shortcuts becomes especially powerful, because space appears almost designed to provoke that dream. Take the nearest star beyond our sun. Even traveling faster than any spacecraft humanity has ever built, the journey would require tens of thousands of years, not months, not decades, thousands of years. Entire civilizations could rise and fall before arrival. The numbers become difficult to emotionally process. Human intuition simply wasn't built for scales like this. We're comfortable with kilometers. We can imagine cities. We can imagine countries. Light years are another matter entirely. As a result, our minds naturally search for alternatives. Surely there must be another way. Surely there must be a route we haven't discovered. Surely the universe cannot be quite that inconvenient. Of course, the universe has never shown much concern for human convenience. Nevertheless, the search continues. This tendency appears frequently in science fiction. Long before physicists seriously discussed wormholes, writers imagined various forms of faster-than-light travel. Some invented hyperspace, others proposed jump gates, still others described hidden dimensions. The specific mechanisms differed, but the underlying motivation remained remarkably consistent. Distance creates a problem. A shortcut provides a solution. Science fiction often functions as a laboratory for ideas. Writers explore possibilities before technology catches up. Sometimes the ideas remain fictional. Occasionally, they inspire real innovation. Submarines appeared in fiction before becoming practical realities. Communication devices resembling smartphones appeared decades before their invention. The boundary between imagination and reality can be surprisingly fluid. That does not mean wormholes exist, of course. It simply means humans have spent a long time imagining ways to overcome distance. When physicists eventually discovered mathematical structures resembling cosmic shortcuts, public fascination arrived almost immediately. People were already primed for the concept. The dream existed first. The mathematics came later. Another reason shortcuts appeal to us involves something more personal. Time. Distance and time are closely related. Every long journey consumes both. A shortcut does not merely save effort. It saves part of a life. Imagine two routes between the same destinations. One requires 10 hours. The other requires 10 minutes. Most people instinctively choose the second option. Not because they dislike travel, because time feels valuable. The older we become, the more aware we often become of this fact. Hours matter, days matter, years matter. Every shortcut effectively returns a portion of life. Perhaps that is why shortcuts generate such strong emotional responses. They offer efficiency, certainly, but they also offer possibility. The hours saved can be spent elsewhere. The effort saved can be used elsewhere. A shortcut expands what feels achievable. In this sense, wormholes represent the ultimate shortcut, not merely reducing a journey, but potentially eliminating it. A trip requiring millions of years might become instantaneous. An impossible destination might become accessible. The idea pushes the concept of a shortcut to its absolute extreme. Yet even if wormholes never exist physically, they reveal something meaningful about human thinking. We're constantly searching for connections. We seek patterns. We seek roots. We seek solutions. When confronted by vast distances, our first instinct is rarely acceptance. Instead, we start asking questions. Could there be another way? Could there be something hidden? Could there be a route nobody has discovered yet? Many of humanity's greatest achievements began with exactly those questions. Flight seemed impossible. People pursued it anyway. Crossing oceans seemed dangerous. People attempted it anyway. Reaching space seemed absurd. People accomplished it anyway. Curiosity repeatedly pushes against apparent limitations. Sometimes the limitations remain, sometimes they do not. This is one reason scientists remain interested in wormholes despite the enormous challenges involved. The idea may sound fantastical, but so did many other discoveries before evidence arrived. Science progresses by investigating possibilities rather than dismissing them outright. Of course, possibilities require evidence. Wishful thinking alone proves nothing. A dream remains a dream until observation supports it. That distinction matters greatly. Scientists do not study wormholes because they hope wormholes exist. They study them because the mathematics suggests the possibility deserves examination. The difference is important, yet it is difficult to deny the emotional appeal. There is something undeniably exciting about the possibility that the universe might contain hidden pathways. Not because we know they exist, because we do not know. Uncertainty creates room for exploration, and exploration has always occupied a special place in human history. From the earliest migrations across continents to modern robotic missions exploring distant planets, our species repeatedly moves toward the unknown. Sometimes the motivation is survival, sometimes opportunity, sometimes simple curiosity. Often it is all three. Wormholes sit at the intersection of those instincts. They represent an unknown possibility tied directly to exploration. If they exist, they could transform our understanding of distance. If they do not, studying them still teaches us something about space-time itself. Either outcome provides value. Meanwhile, the dream continues. A dream older than physics, older than astronomy, perhaps even older than civilization itself. The dream that somewhere beyond the obstacles, beyond the mountains, beyond the oceans, beyond the stars, there might be a hidden route waiting to be discovered. And as humanity's understanding of the universe gradually improved, that ancient dream began colliding with a surprising realization. The real obstacle might not be technology alone. The real obstacle might be the incredible size of the cosmos itself. Which brings us naturally to the next question. Just how large is the universe we're trying to cross in the first place? When people first hear about wormholes, the reaction is often immediate. That sounds useful, and honestly, it is difficult to disagree. If someone offered you a doorway that could instantly transport you across the galaxy, most practical concerns would probably take a back seat for at least a few moments. You might have questions, certainly. You might wonder whether it was safe. You might wonder whether it actually worked. But somewhere in the back of your mind, another thought would likely appear that would save an incredible amount of travel time. The reason wormholes sound so appealing is actually very simple. Space is unbelievably large. Not large in the everyday sense, not even large in the global sense. Space is so vast that many of the numbers involved stop feeling meaningful to the human brain. We can read them, we can write them, we can calculate them, but truly understanding them emotionally is another matter entirely. Human beings evolved in a world of relatively short distances. A few kilometers mattered. A few dozen kilometers mattered even more. Entire civilizations developed within regions that could be crossed on foot. Our intuition was built around landscapes, rivers, forests, and coastlines. Nobody evolved to naturally understand the distance between stars. As a result, our brains often underestimate just how empty and enormous the universe really is. Let's start somewhere familiar. Imagine standing on Earth and looking upward on a clear night. The stars appear scattered across the sky. Some seem brighter, some seem dimmer. Many appear close together. At first glance, the heavens can almost resemble a giant ceiling decorated with points of light. The reality is much stranger. Those stars are separated by distances so vast that even light struggles to cross them. Take the moon, for example. The moon often feels close. After all, it dominates the night sky. People have looked at it for thousands of years. Poets have written about it. Scientists have studied it. Astronauts have visited it. Compared to the rest of the universe, the moon is practically next door, and yet it remains approximately 384,000 kilometers away. If you could drive a car continuously toward the moon at highway speeds without stopping for fuel, food, sleep, or the obvious problem of there being no road through space, the journey would take many months already. The scale begins to feel unusual. Now let's move outward. The sun sits about 150 million kilometers from Earth. Light itself requires around 8 minutes to make the trip. Every sunrise you have ever witnessed actually happened 8 minutes before you saw it. The sunlight reaching your eyes began its journey while you were still doing something else entirely. Maybe making coffee, maybe reading, maybe sleeping. 8 minutes isn't particularly long, but remember what we're discussing. That's the travel time for light, the fastest thing known to exist. Nothing moves faster. Nothing even ties for first place. Light occupies that position alone. If light needs 8 minutes to reach the sun, ordinary transportation begins looking very inadequate. A modern passenger aircraft would need many years to cover the same distance. The fastest spacecraft humanity has ever built would still require months. And remarkably, we haven't even left our local neighborhood yet. The truly staggering distances begin once we leave the solar system. The nearest star beyond our sun is Proxima Centauri. Astronomers often describe its distance as approximately 4.24 light-years. That number sounds manageable until you remember what a light-year actually means. A light-year is not a measure of time, it's a measure of distance. Specifically, the distance light travels in 1 year. Light moves at roughly 300,000 kilometers every second, not every minute, every second. In the time it takes to blink, light can travel around Earth multiple times. Even moving at that incredible speed, it still requires more than 4 years to reach Proxima Centauri. That fact alone reveals something profound. The universe is not merely big, it is separated. Distances are not just large, they are obstacles. Consider humanity's greatest achievements in transportation. Ships crossed oceans, railways connected continents, aircraft shrank the world dramatically. Each innovation reduced travel times. Places that once seemed remote became accessible. Journeys that consumed months became routine. Then we encountered interstellar space. Suddenly progress slowed. Not because engineers lacked creativity, not because scientists stopped trying, because the scale became almost absurd. Suppose humanity developed a spacecraft capable of traveling 10 times faster than anything currently available. That would be an extraordinary accomplishment. History books would celebrate it. Engineers would become legends. The achievement would transform space exploration. And yet Proxima Centauri would still remain astonishingly far away. A journey could require thousands of years. Not decades, not centuries, thousands. Entire languages might evolve during the voyage. Governments could appear and disappear. Civilizations could transform beyond recognition. The travelers might depart from a world that no longer exists by the time they arrive. This is where the problem becomes clear. Space does not merely challenge transportation. Space challenges time itself. Imagine planning a vacation that lasts several thousand years. The logistics become somewhat complicated. Packing alone would be a nightmare. Even the most optimistic travel brochure might struggle with that itinerary. Yet this challenge grows even larger when we look beyond nearby stars. Our galaxy, the Milky Way, contains hundreds of billions of stars. That number is difficult enough to comprehend. The galaxy itself stretches roughly 100,000 light-years across. To appreciate how enormous that is, imagine shrinking Earth until it becomes the size of a grain of sand. At that scale, the Milky Way would still be extraordinarily large. The comparisons begin breaking down because human experience provides no useful reference point. The galaxy exceeds ordinary understanding, and the Milky Way is not unusual. It is merely one galaxy among countless others. Beyond it lies the Andromeda Galaxy, approximately 2.5 million light-years away. The light reaching Earth from Andromeda tonight began its journey before human beings existed in their modern form. Think about that for a moment. When that light started traveling toward us, humanity as we know it had not yet appeared. Civilizations had not formed, cities did not exist, written language had not emerged, agriculture had not begun. Yet the light continued moving year after year, century after century, millennium after millennium. Only now does it arrive. That is the scale we're dealing with. This is why physicists become interested in shortcuts. Not because shortcuts sound convenient, because conventional travel appears almost hopeless when applied to cosmic distances. If humanity ever dreams of reaching other stars regularly, the challenge is not merely building better engines. The challenge is the enormous size of the universe itself. The situation becomes even more interesting when we consider the speed of light. At first glance, light seems incredibly fast, and it is. Nothing outruns it. Nothing even comes close. Yet the universe is so vast that even light appears slow. That statement sounds contradictory. How can the fastest thing in existence seem slow? Because speed and distance always work together. A fast vehicle crossing a parking lot arrives quickly. The same vehicle crossing an ocean requires more time. The same principle applies to light. The universe is simply so large that even maximum speed struggles to overcome the distances involved. Imagine receiving a message from a civilization located 1,000 light years away. The message would require 1,000 years to arrive. Your reply would require another 1,000 years. A simple conversation would consume 2 millennia. By the time the exchange concluded, entire eras of history could pass. Communication itself becomes difficult. Travel becomes even harder. This realization gradually transformed astronomy during the 20th century. As telescopes improved, scientists discovered a universe far larger than previous generations had imagined. Every improvement seemed to reveal additional distance, more stars, more galaxies, more empty space. The horizon kept expanding. Instead of making the cosmos feel smaller, knowledge often made it feel larger. The observable universe currently extends for billions of light years in every direction. The numbers involved become so extreme that scientists often use specialized units simply to keep calculations manageable. Ordinary measurements become inconvenient. The universe essentially forces us to invent larger ways of counting. Interestingly, this enormous scale creates a kind of loneliness. Not emotional loneliness necessarily, geometric loneliness. Everything is separated. Stars are separated. Planets are separated. Galaxies are separated. Even within our own solar system, distances remain surprisingly large. Science fiction films sometimes portray spacecraft weaving effortlessly between planets as though they were neighboring towns. Reality looks quite different. The planets are separated by vast regions of emptiness. Most of the solar system consists not of objects but of space. Space dominates. Matter occupies only a tiny fraction of the total volume. In fact, if you remove the planets, moons, asteroids, and every other visible object, most of the solar system would look almost unchanged. The emptiness is the primary feature. This surprises many people because illustrations often compress distances dramatically. Educational diagrams must fit onto pages and screens. If they displayed the solar system accurately, many planets would become tiny dots separated by enormous blank regions. The emptiness would overwhelm the image. In a sense, the universe is defined as much by what is absent as by what is present. There are stars, there are galaxies, there are planets, but between them lies staggering emptiness. That emptiness creates the distance problem, and the distance problem creates the appeal of wormholes. A wormhole represents a possible solution to the greatest obstacle in space exploration. Not fuel, not engineering, not life support. Distance itself. Imagine drawing 2 points on opposite ends of a piece of paper. Traveling normally means moving across the surface. The route is long. The journey takes time. Now fold the paper. The points touch. Distance effectively disappears. The traveler does not move faster. The geometry changes. That simple idea explains why wormholes remain so fascinating. They attack the problem directly. Instead of trying to move through space faster, they potentially change the structure of space itself. It's a profoundly different approach, and perhaps the only approach capable of addressing distances on a truly cosmic scale. Of course, recognizing a problem does not guarantee a solution. The universe has never promised convenience. Many beautiful ideas turn out to be impossible. Others remain theoretically possible but practically unreachable. Wormholes may belong to either category. Scientists still do not know. Yet the sheer size of the universe ensures the question remains worth asking. Because every time we look upward, every time we observe distant stars, every time we discover another world orbiting another sun, the same challenge remains waiting. How do you cross distances this large? How do you bridge gaps measured in light years? How do you explore a cosmos where even light requires years, centuries, or millions of years to travel between destinations? Those questions eventually led physicists toward a surprising possibility. A possibility hidden inside the geometry of spacetime itself. And understanding that possibility begins with a deceptively simple thought experiment. involving nothing more complicated than a sheet of paper. Take a sheet of paper for a moment. Not literally, of course. You're hopefully comfortable, perhaps already beginning to relax, and there is no need to interrupt that by searching for office supplies. Just imagine a simple piece of paper. Now place a small dot near one edge, then place another dot near the opposite edge. These two dots represent locations, perhaps two cities, perhaps two planets, perhaps two stars separated by an impossible gulf of empty space. The exact locations don't matter. What matters is the distance between them. If someone wanted to travel from one dot to the other, the solution seems obvious. You move across the surface, step by step, little by little. The route may be long, but there's only one apparent way to complete it: travel through the distance separating the 2 points. That sounds so simple that it hardly seems worth discussing. And yet, hidden inside this ordinary piece of paper is one of the most important ideas behind wormholes, because now we do something interesting. We fold the paper. Suddenly, the 2 dots that once occupied opposite ends now touch each other. The distance across the surface still exists. Nothing about the paper has been removed. The long route remains available, but another possibility has appeared: a shortcut. Instead of traveling across the entire sheet, you simply move directly from one touching point to the other. The journey becomes dramatically shorter. Not because you moved faster, not because you discovered a better vehicle, not because you broke any laws of motion. The geometry changed, and that simple realization sits at the heart of the wormhole concept. Distance depends on the shape of the space you're moving through. That may sound obvious at first. After all, roads work exactly the same way. A straight road is shorter than a winding one. A bridge can eliminate a detour. A tunnel can reduce travel distance through a mountain. The geometry of a route affects the journey. But when physicists began studying space-time during the 20th century, they discovered something extraordinary. Space itself might possess geometry, not merely objects inside space, but space itself. For most of human history, people imagined space as a kind of empty container, a giant stage upon which the universe performed. Stars moved, planets moved, galaxies moved, but space itself remained passive, empty, featureless, unchanging. That picture seems perfectly reasonable. After all, when we look around, space doesn't appear to be doing anything. The room you're sitting in doesn't seem to bend. The sky overhead doesn't appear flexible. The distance between 2 locations feels fixed and dependable, yet appearances can be misleading. One of the great revolutions in physics occurred when scientists realized that space might not be an inert backdrop at all. Instead, it could possess structure, shape, geometry, behavior. And if space possesses geometry, then geometry can potentially change. That possibility opens a remarkable door. Before Albert Einstein developed general relativity, gravity was usually described as a force. Objects attracted one another. Planets orbited stars because gravity pulled them. The explanation worked quite well. In fact, it worked so well that many people assumed the story was essentially complete. Then Einstein arrived and proposed something much stranger. What if gravity wasn't really a force? What if planets weren't being pulled? What if space-time itself was curved? At first glance, this idea sounds almost absurd. Curved into what? How does space bend? What exactly is it bending through? These questions puzzled many physicists when the theory first appeared. Yet the mathematics proved remarkably successful. Einstein suggested that massive objects alter the geometry of space-time around them. A star changes it. A planet changes space-time. A galaxy changes space-time. The larger the mass, the stronger the effect. A useful analogy involves a stretched rubber sheet. Imagine placing a heavy bowling ball in the center. The sheet sinks downward. Now roll a smaller ball nearby. Instead of moving in a straight line, it follows the curvature. Its path changes because the surface itself has changed. Of course, space-time is not literally a rubber sheet. The analogy is imperfect. Every analogy eventually breaks down, but it helps illustrate a crucial point. Objects follow the geometry around them. If geometry changes, motion changes. Gravity emerges naturally from the shape of space-time. This was an extraordinary revelation. The universe suddenly appeared far more dynamic than anyone had suspected. Space was not merely sitting there doing nothing. It could stretch, it could curve, it could evolve. And if it could curve, physicists naturally began asking questions. How much can it curve? What shapes are possible? Are there limits? Could geometry become so unusual that distant regions of the universe somehow touch? Those questions eventually led researchers into increasingly strange territory. One of the most fascinating aspects of science is that discoveries often emerge accidentally. Scientists set out to solve one problem and stumble into another. They begin exploring one idea and unexpectedly uncover something entirely different. The story of wormholes follows this pattern. Physicists weren't trying to invent shortcuts across the cosmos. They were investigating Einstein's equations. Those equations turned out to be surprisingly imaginative. Again and again, researchers discovered strange solutions hidden within them. Black holes emerged from the mathematics. Expanding universes emerged from the mathematics. And eventually, structures resembling bridges through space-time emerged as well. The equations seemed to allow situations where two distant locations could become connected, not metaphorically, geometrically. The possibility was startling. Remember our folded sheet of paper? That analogy suddenly became more than a simple teaching tool. It became a rough illustration of something the mathematics appeared to permit. Perhaps two distant regions of space-time could become connected through a shortcut, not because space was destroyed, not because distance disappeared, because geometry changed. This idea challenges intuition. Human beings are accustomed to thinking about distance in straightforward terms. If two cities are separated by 100 kilometers, then 100 kilometers must be crossed. This statement feels almost self-evident. Yet geometry occasionally surprises us. Consider Earth's surface. Imagine standing at the equator and traveling due north. Another traveler begins elsewhere along the equator and also heads due north. Initially, the two travelers move along parallel routes, yet eventually they meet at the North Pole. Their paths converged because the geometry of Earth's surface differs from the geometry of a flat plane. The shortest route between locations depends on the shape of the space involved. This principle becomes even more important in relativity. Space-time possesses geometry, and geometry influences distance. The realization feels subtle at first, then its implications begin expanding. If geometry can influence distance, perhaps distance is not quite as absolute as it appears. Perhaps what seems unimaginably far under one geometry could become much closer under another. Suddenly, the concept of a shortcut no longer sounds entirely ridiculous. Difficult, certainly. Exotic, absolutely. But ridiculous, not necessarily. Interestingly, many people assume wormholes involve faster than light travel. That's understandable. Popular culture often presents them that way. Yet the underlying idea is actually different. A wormhole does not necessarily require traveling faster than light. Instead, it potentially reduces the distance that must be traveled. Imagine two towns separated by a mountain. Traveling over the mountain requires a long journey. Building a tunnel shortens the route. Nobody travels faster. The path simply becomes shorter. The tunnel changes geography. A wormhole would do something similar on a far grander scale. The traveler might move at ordinary speeds. The route itself becomes different. That distinction matters because Einstein's relativity places strict limits on speed. Nothing can simply accelerate beyond the speed of light. Physics appears quite firm on that point. Wormholes became interesting partly because they seemed to offer a possible workaround, not by violating the rules, but by taking advantage of geometry. Of course, recognizing a possibility in mathematics and building one in reality are entirely different matters. Human beings can write equations describing all sorts of situations. Some correspond to nature, some do not. The universe remains the final judge. Nevertheless, theoretical possibilities matter. Many scientific discoveries begin as mathematical curiosities. At first, they appear abstract. Then evidence arrives. Black holes provide a wonderful example. When scientists first encountered black hole solutions in Einstein's equations, many found them suspicious. The objects seemed too strange, too extreme, too bizarre. For years, some researchers doubted whether they could truly exist. Today, black holes occupy a central place in astronomy. Observations confirm them repeatedly. Images have even been captured of their surroundings. The lesson is not that every strange equation describes reality. The lesson is that strange equations deserve investigation. Sometimes nature turns out to be stranger than expected. Wormholes occupy a similar position today. They remain hypothetical. No confirmed observation exists. No telescope has definitively detected one. No spacecraft has flown through one. No tourist brochures advertise weekend trips through interstellar tunnels. Yet the mathematics continues attracting attention. And one reason is that the underlying idea remains surprisingly elegant. Distance depends on geometry. Geometry can change. Therefore, distance might change. The logic is simple. The consequences are extraordinary. What's especially fascinating is how quickly this idea reshapes our understanding of the universe. Most of us spend our lives assuming that separation is permanent. The stars appear distant because they are distant. Galaxies appear remote because they are remote. Space seems vast because it is vast. Wormholes introduce a subtle complication. What if apparent distance isn't the whole story? What if geometry matters as much as measurement? What if two locations that appear impossibly far apart are connected in ways we don't yet understand? Again, none of this proves wormholes exist. Science requires more than intriguing possibilities. Evidence remains essential. Still, the concept encourages a different way of thinking about space. Instead of imagining the universe as a rigid framework, we begin imagining it as something dynamic, flexible, structured, capable of surprising behavior. This shift in perspective was one of Einstein's greatest gifts to physics. He transformed space from a passive stage into an active participant. And once that transformation occurred, entirely new possibilities emerged. Some of those possibilities eventually became established science. Others remain open questions. Wormholes belong firmly in that second category. They sit at the boundary between known physics and unresolved mystery. By the early 20th century, physics was facing a problem. Actually, it was facing several problems. For centuries, Isaac Newton's description of gravity had worked remarkably well. Planets orbited the sun. Apples fell from trees. The moon circled Earth. Engineers, astronomers, and mathematicians relied on Newton's equations with tremendous success. If you wanted to calculate the motion of a cannonball, Newton could help. If you wanted to predict the orbit of a planet, Newton could help. If you wanted to understand why objects fall downward instead of drifting into the sky, Newton could help with that too. For more than 200 years, his framework dominated science. Yet occasionally, tiny cracks began appearing. Not dramatic cracks, nothing obvious enough to overthrow an entire scientific worldview. Just small inconsistencies, little puzzles, subtle observations that didn't quite fit. Science often progresses this way. Major evolutions rarely begin with giant flashing warning signs. Instead, they begin with details, a measurement that seems slightly wrong, an observation that refuses to cooperate, a prediction that misses by just a little. One of the most famous examples involved the planet Mercury. Mercury orbits closer to the Sun than any other major planet. Astronomers tracked its movement carefully and noticed something unusual. The orbit wasn't behaving exactly as Newton's equations predicted. The difference was tiny, almost insignificant. Yet it persisted. Scientists proposed various explanations. Perhaps another unseen planet existed. Perhaps measurements were inaccurate. Perhaps something else was influencing Mercury's motion. Years passed. The puzzle remained. At the same time, another mystery was growing. Light behaved strangely. Experiments suggested that the speed of light remained constant regardless of the observer's motion. That result was deeply unsettling. According to traditional thinking, speed should add together. If you're standing still and a car drives past, you measure one speed. If you're running toward the car, you measure a different speed. That seems perfectly reasonable, yet light refused to cooperate. No matter how scientists measured it, the speed remained the same. The universe appeared to be protecting this number with extraordinary determination. Physicists found themselves in an uncomfortable position. Their theories worked incredibly well, but certain observations seemed to be pointing toward something deeper. Enter Albert Einstein. At the time, Einstein was not a famous celebrity scientist. He wasn't directing major research institutes. He wasn't surrounded by teams of assistants. In fact, he worked at a patent office in Switzerland. His daily responsibilities involved evaluating inventions. Not exactly the environment most people associate with revolutionizing our understanding of reality. Yet extraordinary ideas sometimes emerge from unexpected places. Einstein possessed a remarkable ability. He could take familiar assumptions and examine them from unusual angles. Instead of asking, "What do we know?" he often asked, "What if we've misunderstood something fundamental?" That approach led him toward one of the most important scientific breakthroughs in history. In 1905, Einstein published what would later become known as special relativity. The theory transformed physics. Space and time, previously considered separate entities, became intertwined. Events that seemed absolute turned out to depend on motion. Time itself could slow down, lengths could shrink, simultaneity became relative. The universe suddenly appeared far stranger than anyone had imagined. Yet, as revolutionary as special relativity was, it contained an important limitation. It didn't fully explain gravity. Einstein knew this, and he became obsessed with solving the problem. Gravity had resisted explanation for centuries. Replacing Newton's framework would require something extraordinary. Eventually, Einstein realized that the problem might not involve gravity itself. Perhaps the problem involved space and time. Imagine you're standing inside an elevator. Suddenly, the elevator begins accelerating upward. You feel pressed against the floor. From inside, it feels remarkably similar to standing in a gravitational field. That observation fascinated Einstein. The more he thought about it, the more significant it appeared. Could gravity and acceleration somehow be related? Could they actually be different aspects of the same phenomenon? This simple insight eventually led him toward general relativity. Published in 1915, general relativity fundamentally changed how scientists understood reality. Before Einstein, gravity was usually treated as a force. After Einstein, gravity became geometry. This shift was profound. Instead of imagining invisible forces pulling objects together, Einstein described matter and energy changing the shape of space-time itself. Massive objects bend space-time. Planets follow the resulting curves. Stars create larger distortions. Galaxies create larger distortions still. Gravity emerges naturally from geometry. It's one of those ideas that sounds strange at first. Then it becomes difficult to imagine reality any other way. The beauty of general relativity lies partly in its elegance. Rather than adding complicated mechanisms, Einstein simplified the picture. Space and time became dynamic, flexible, responsive. The universe transformed from a rigid framework into something far more interesting. And this is where wormholes quietly enter the story. Not immediately, not dramatically, certainly not with anyone announcing, "Let's invent a tunnel through the universe." Instead, they emerged accidentally. That word is important. Accidentally. Einstein wasn't searching for cosmic shortcuts. He wasn't attempting to solve interstellar transportation. He wasn't trying to help future science fiction writers. His goal was understanding gravity. Yet when physicists began exploring the mathematical consequences of general relativity, they encountered surprises, many surprises. General relativity is governed by a collection of equations known as the Einstein field equations. These equations describe how matter, energy, space, and time interact. They're famously complex. Even today, solving them remains challenging. Yet within those equations lurked possibilities nobody expected. Some solutions described black holes, others described expanding universes. Still others described rotating space-time. Again and again, the mathematics produced strange outcomes. Many seemed almost unbelievable. The equations behaved like an enormous unexplored landscape. Scientists would travel into one region and discover a new phenomenon. Then they'd explore another region and find something even stranger. In some ways, general relativity became a map of possibilities. Reality would determine which possibility actually existed. But first, they had to be discovered mathematically. One of the earlier surprises involved black holes. Today, black holes appear frequently in documentaries, books, and news articles. They have become familiar. But when physicists first encountered them, the reaction was very different. Many researchers found the concept absurd. Objects so dense that not even light could escape. That sounded extreme, almost ridiculous. Yet the mathematics allowed it. Over time, evidence accumulated. Observations improved. Black holes gradually moved from speculation to accepted science. This process taught physicists an important lesson. The universe does not care whether an idea feels intuitive. Nature follows its own rules. If mathematics and evidence point towards something strange, scientists must take it seriously. That lesson became particularly important as researchers continued investigating Einstein's equations. Among those researchers was Einstein himself. In the 1930s, he collaborated with a physicist named Nathan Rosen. Together, they explored certain solutions within general relativity. Their goal was not creating a transportation system. Rather, they were attempting to understand fundamental features of space-time. During this work, they encountered a remarkable possibility. Certain mathematical structures appeared capable of connecting separate regions of space-time. The details were complicated. The implications were extraordinary. Instead of existing as isolated locations, distant points could potentially become linked through a kind of bridge. Today, this structure is known as the Einstein-Rosen bridge. At the time, nobody called it a wormhole. That term would arrive later. Nevertheless, the basic concept had appeared. A connection, a shortcut, a bridge through space-time itself. The discovery wasn't greeted with universal excitement. In fact, many physicists initially regarded it as little more than a mathematical curiosity. Interesting perhaps, useful perhaps, but not necessarily physical. Mathematics frequently generates solutions that don't correspond to reality. A solution can exist on paper without existing in nature. Scientists needed to determine which category these bridges belonged to. Still, the idea refused to disappear, partly because it emerged naturally from respected physics, partly because it was so intriguing, and partly because it hinted at something humanity had imagined for centuries: a shortcut. What makes the story especially fascinating is that Einstein himself wasn't particularly enthusiastic about wormholes as transportation devices. Popular culture often portrays him as opening the door to interstellar travel. Reality was more restrained. Einstein approached these structures primarily as mathematical objects. He wasn't writing adventure stories. He was exploring geometry. The dramatic implications came later. Other physicists examined the bridges and began asking new questions. Could anything pass through them? Could they remain stable? Could they connect distant regions? Could they connect different times? Each question generated more questions. The mystery grew. Meanwhile, general relativity continued proving itself correct. One prediction after another received observational support. Mercury's orbit matched Einstein's calculations. Light bent around massive objects exactly as predicted. Time slowed near strong gravitational fields. The theory repeatedly demonstrated its accuracy. This success made its stranger implications hard to ignore. If general relativity correctly describes reality, then its unusual possibilities deserve attention, not blind acceptance, but attention. Science requires careful distinction between possibility and fact. The equations might permit something. Nature might not. Evidence remains essential, yet possibility matters. Without possibility, there is nothing to investigate. Wormholes survived because they remained mathematically possible. No observation eliminated them. No theorem completely prohibited them. They occupied an intriguing middle ground, neither confirmed nor dismissed. And that status continues today. What's particularly remarkable is how a theory designed to explain gravity ultimately transformed our understanding of distance itself. Before Einstein, space seemed straightforward. Locations were separated by measurable intervals. Travel required crossing those intervals. After Einstein, geometry became flexible. Distance became more subtle. The universe acquired hidden complexity. Imagine living in a world where roads occasionally folded in unexpected ways. A city appearing hundreds of kilometers away might secretly be much closer through an undiscovered route. That's not exactly how wormholes work, but it captures part of the surprise physicists experienced. The geometry of space-time could be richer than expected, much richer. And once that realization occurred, researchers became increasingly curious about what other surprises might be hiding within Einstein's equations. The Einstein-Rosen bridge represented only the beginning. It was the first glimpse of a possibility, not necessarily a practical possibility, not necessarily a real one, but a possibility nonetheless. As scientists studied these bridges more carefully, they encountered a significant problem. The original Einstein-Rosen bridge wasn't quite the convenient shortcut people imagined. In fact, it appeared to be fundamentally unusable. A traveler attempting to cross would encounter serious difficulties. The bridge seemed unstable, temporary, more mathematical than practical. Yet rather than ending the story, this challenge opened an entirely new chapter in the investigation. Because once physicists understood the limitations of the original bridge, they began asking a different question. What would a truly usable wormhole require? By the mid-1930s, Albert Einstein had already changed physics forever. General relativity had survived increasingly rigorous tests. Astronomers were discovering that the theory worked. Physicists were realizing that space and time were not passive backgrounds but active participants in the structure of reality. The universe had become far stranger than anyone imagined during Newton's era. Yet Einstein himself remained dissatisfied with certain aspects of his theory. This often surprises people. When we look back at scientific breakthroughs, it's easy to imagine their creators celebrating a finished masterpiece. Reality is usually messier. Scientists solve one problem and uncover 10 new ones. Answers create questions. Solutions reveal deeper mysteries. Einstein was no exception. Even after developing general relativity, he continued searching for a deeper understanding of nature. One particular issue bothered him. At the center of some solutions to his equations lurked something called a singularity. A singularity is a place where the mathematics appears to break down. Physical quantities become infinite. Predictions stop making sense. The equations essentially throw up their hands and refuse to continue. Physicists generally dislike infinities. Not because infinities are automatically wrong, because infinities often signal that something important is missing from our understanding. Imagine calculating the height of a tree and obtaining an answer of infinite meters. The result would immediately raise suspicion. You wouldn't conclude that the tree stretches endlessly into space. You would assume something had gone wrong with the calculation. Einstein felt similarly about singularities. The mathematics of black holes seemed to contain regions where spacetime behaved in extreme ways. He wondered whether there might be another interpretation, another structure hidden within the equations, another way of understanding what was happening. This curiosity eventually led him to collaborate with Nathan Rosen, a physicist working at the Institute for Advanced Study in Princeton. Together, they examined one of the simplest black hole solutions available at the time. The solution had originally been discovered by the German physicist Karl Schwarzschild shortly after Einstein published general relativity. Schwarzschild achieved something remarkable. While serving during World War I, he found an exact solution to Einstein's extraordinarily difficult equations. That solution described the space-time surrounding a spherical mass. Today, it forms the foundation of much black hole physics. At the time, however, its implications were not fully understood. Einstein and Rosen looked carefully at this solution and noticed something interesting. The mathematics seemed to permit a structure connecting two separate regions of space-time. Rather than ending abruptly at a singular point, space-time could potentially continue into another region entirely. The result resembled a bridge. Not a bridge made of steel, not a bridge made of concrete, a bridge made of geometry, a connection formed by space-time itself. This became known as the Einstein-Rosen bridge. Today, many people refer to it as the first wormhole. That description is not entirely perfect, but it's close enough for our purposes. The important point is that scientists had discovered a mathematical structure capable of linking distant regions together. For the first time, the possibility of a shortcut through space-time had emerged from respected physics. Not speculation, not fantasy, not mythology, mathematics. Of course, discovering a bridge on paper and building one in reality are very different things. That distinction cannot be emphasized enough. Nature frequently allows mathematical possibilities that never actually occur. The universe contains many potential arrangements. Only some become physically real. Yet even as a mathematical object, the Einstein-Rosen bridge was fascinating. Imagine standing on one side of a mountain. You want to reach the other side. Normally, you climb over it. The journey is long. The route is difficult. Now imagine discovering a tunnel passing directly through the mountain. The destination remains the same. The distance changes dramatically. The Einstein-Rosen bridge suggested something similar might occur within space-time. Two apparently separate locations could become connected through a shortcut. Travelers would not need to cross the entire intervening distance. They would pass through the bridge instead, at least in theory. The phrase "at least in theory" turns out to be extremely important. Because as physicists examined the bridge more carefully, problems began appearing, very serious problems. The original Einstein-Rosen bridge was not the convenient cosmic highway that science fiction stories would later popularize. In fact, it was astonishingly impractical. To understand why, imagine a tunnel that collapses the instant you try to enter it. Technically, the tunnel exists. Technically, it connects two locations. Technically, a shortcut is present, yet nobody can actually use it. That captures much of the difficulty. The Einstein-Rosen bridge appeared unstable. The connection formed, then it pinched off almost immediately. The geometry closed faster than anything could pass through. A traveler approaching the bridge would never successfully emerge on the other side. The shortcut existed mathematically but remained inaccessible physically. This realization disappointed many researchers. For a brief moment, the dream of traversable wormholes seemed within reach. Then the details intervened. As often happens in physics, the universe proved less accommodating than initial hope suggested. Still, the bridge remained important. Even if nobody could cross it, it demonstrated something profound. Einstein's equations genuinely permitted connections between different regions of space-time. That possibility alone was extraordinary. Before general relativity, the concept would have seemed nonsensical. After general relativity, it became a legitimate area of investigation. The bridge transformed wormholes from fantasy into physics. Not established physics, not observed physics, possible physics. That distinction matters. Scientific progress often begins with possibilities. Researchers discover something allowed by theory, then they investigate whether reality agrees. Some possibilities survive, others disappear. The process takes time. What makes the Einstein-Rosen bridge especially interesting is that it emerged naturally. Nobody inserted it deliberately. Nobody modified the equations to create it. The structure simply appeared. It's a bit like exploring a cave system and unexpectedly finding an enormous hidden chamber. You weren't searching for it, yet there it is, waiting. The discovery forces you to rethink the entire landscape. Physicists experienced something similar. The bridge revealed that space-time could possess a richness previously unimagined. Space was not merely a vast emptiness separating objects. Space could have structure, topology, connections, hidden complexity. Those ideas would eventually influence entire generations of researchers. Yet during the early years, uncertainty remained. Scientists debated what the bridge actually meant. Some regarded it as a mathematical curiosity. Others viewed it as a clue pointing toward deeper truths. Still others suspected that future theories would eliminate it entirely. Nobody knew, and uncertainty creates fertile ground for scientific exploration. As the decades passed, researchers continued investigating. One question kept returning. Could a bridge ever be made traversable? In other words, could a wormhole remain open long enough for something to cross? The challenge proved formidable. Every calculation seemed to encounter obstacles. The geometry wanted to collapse. Gravity worked against stability. The bridge behaved less like a tunnel and more like a trap. Yet the idea refused to disappear. Partly because it was intellectually intriguing, partly because it raised fascinating questions about space-time, and partly because the implications were so dramatic. Imagine for a moment that traversable wormholes actually existed. The consequences would be difficult to overstate. Distances measured in light years could become manageable. Regions of the galaxy separated by enormous gaps might become neighbors. Interstellar exploration would be transformed. Human civilization itself could change fundamentally. Of course, those possibilities remain speculative. No evidence suggested usable wormholes existed. Nevertheless, physicists could not ignore the implications. Whenever a theory permits something extraordinary, curiosity follows naturally. The Einstein-Rosen bridge also introduced scientists to an important lesson about space-time. Geometry can behave in surprisingly non-intuitive ways. Our everyday experience teaches us to think about space as straightforward. Distance appears fixed, locations appear separate, routes appear obvious. General relativity challenges all of those assumptions. Space-time becomes dynamic, flexible, capable of unexpected configurations. The bridge represented one of the earliest and most dramatic examples. Another fascinating aspect of the story involves black holes. Today, wormholes and black holes are often discussed together. That relationship is not accidental. The original Einstein-Rosen bridge emerged from black hole mathematics. For many years, scientists wondered whether black holes might somehow contain wormholes. The idea captured imaginations immediately. After all, black holes already seemed mysterious. Adding hidden tunnels only increased the intrigue. Yet nature once again proved difficult to interpret. Black holes clearly exist. Observations have confirmed them repeatedly. Wormholes remain uncertain. The relationship between the two remains an active area of theoretical investigation. Some models connect them closely, others do not. The situation remains unresolved. This uncertainty highlights an important feature of science. Knowledge rarely arrives all at once. Discoveries accumulate gradually. Each answer leads to additional questions. The Einstein-Rosen bridge did not solve the mystery of wormholes. It created the mystery. Before the bridge, scientists weren't even sure such structures deserved discussion. Afterward, they became impossible to ignore. Researchers now had a concrete example, a mathematical object, a starting point, the first step of a much longer journey. And that journey would become increasingly strange, because once physicists understood that the original bridge collapsed too quickly for travel, they began asking a new question. What would be required to keep a wormhole open? Suppose for a moment that a wormhole exists. Not a mathematical diagram in a physics paper, not an artist's impression in a documentary, not a special effect in a science fiction film, an actual wormhole. A genuine shortcut through space-time, a tunnel connecting two distant locations somewhere in the universe. The first question most people ask is obvious. Could you travel through it? After all, that's the entire appeal. A wormhole that cannot be crossed is a bit like discovering a bridge suspended across a canyon and then learning it vanishes whenever anyone tries to step onto it. Interesting, certainly. Useful, not particularly. And this brings us to one of the biggest challenges in wormhole physics. Almost every wormhole that emerges naturally from Einstein's equations appears to have a very strong desire to destroy itself. That may sound dramatic, but it captures the situation surprisingly well. Again and again, physicists find that wormholes tend to collapse. Not eventually, not after millions of years, almost immediately. The universe seems determined to close these shortcuts as quickly as possible. To understand why, we need to think carefully about what a wormhole actually is. Imagine a tunnel drilled through a mountain. The tunnel remains open because solid rock surrounds it. The structure is supported, the walls prevent collapse. Now imagine making the tunnel larger and larger. At some point, the surrounding material becomes unable to support the opening. The roof caves in, the tunnel disappears. Something similar happens with wormholes, except instead of rock supporting the structure, we're dealing with space-time itself. The geometry of space-time must somehow maintain an opening, and according to ordinary gravity, that turns out to be extremely difficult. Gravity has a habit of pulling things together. Stars form because gravity pulls matter inward. Planets form because gravity pulls matter inward. Galaxies form because gravity pulls matter inward. Black holes represent gravity taken to an extraordinary extreme. The same tendency creates problems for wormholes. The moment a tunnel forms, gravity begins working against it. The throat of the wormhole, the narrow region connecting the two ends, experiences enormous stresses. The geometry wants to pinch shut. The opening wants to collapse. The shortcut wants to disappear. This realization emerged gradually as physicists studied wormhole solutions in greater detail. The original Einstein-Rosen bridge already suffered from this problem. It existed mathematically, but it closed too quickly for anything to cross. Imagine trying to run through a doorway that slams shut faster than light can travel. That is essentially what researchers encountered. The tunnel appeared. The tunnel vanished. No traveler ever made it through. For a while, this seemed like the end of the story. Perhaps wormholes were simply impossible as transportation systems. Perhaps they could exist only as fleeting mathematical structures. Perhaps nature allowed them briefly before destroying them immediately. Many scientists considered that possibility. It was a reasonable conclusion. After all, physics is under no obligation to provide convenient shortcuts across the universe. Yet curiosity has a remarkable persistence. Researchers continued asking questions. Could there be circumstances where collapse might be prevented? Could some mechanism hold the wormhole open? Could a stable version exist? Those questions eventually led scientists into some of the strangest territory in theoretical physics. Before we get there, though, it helps to appreciate how difficult the problem really is. Let's imagine a traveler approaching a wormhole. Perhaps they're aboard a spacecraft. Perhaps they are the first human being to encounter such an object. Ahead lies the entrance. The destination waits on the other side. The promise is extraordinary. Cross the wormhole and emerge light years away. Maybe thousands of light years, maybe millions. Yet the wormhole itself must remain stable long enough for the journey, and stability turns out to be incredibly demanding. Think about a suspension bridge. A bridge appears simple when viewed from a distance. People walk across, vehicles drive across. Everything seems straightforward. But underneath lies a complex engineering challenge. Forces pull in different directions. Weight must be distributed carefully. Materials must withstand stress. Engineers spend enormous effort preventing collapse. A traversable wormhole would face similar issues, only the engineering problem would involve spacetime itself. Gravity would constantly attempt to close the opening. The geometry would constantly attempt to pinch inward. The structure would require something to counteract those tendencies, and ordinary matter doesn't seem capable of doing the job. This is where things begin becoming truly strange. Normally, gravity attracts. Mass attracts mass. Objects pull on one another. That behavior is deeply familiar. Drop a ball, it falls downward. Throw something upward, eventually it comes back. Gravity acts like a universal attraction. Wormholes appear to require the opposite. Instead of attraction, they need something repulsive, something capable of pushing outward, something capable of resisting collapse. Imagine trying to keep a tunnel open while an enormous force continuously squeezes it shut. You would need supports pushing back. Without them, the tunnel disappears. The same basic principle applies to wormholes. Physicists eventually realized that maintaining a traversable wormhole might require a form of matter unlike anything encountered in everyday life. This hypothetical material became known as exotic matter. The name sounds dramatic, and honestly, it deserves the title. Exotic matter would possess properties very different from ordinary matter. Most importantly, it could potentially create negative energy densities. Now, negative energy sounds like something invented by a science fiction writer after too much coffee. Yet the concept arises naturally within certain areas of physics. The details become mathematically complex, but the basic idea is surprisingly straightforward. Ordinary energy contributes positively. Exotic configurations could contribute negatively. If enough negative energy existed in the right place, it might counteract gravitational collapse. The wormhole throat could remain open. The tunnel could persist. The shortcut might become traversable. Notice how many words in that paragraph involve possibility, might, could, potentially. Those words matter. Scientists have not discovered warehouses filled with exotic matter. Nobody has located a convenient supply. No engineer currently knows how to manufacture it. The concept emerges from theoretical considerations rather than practical experience. Yet the idea remains important because it demonstrates something fascinating. Physics does not completely forbid traversable wormholes. The equations leave the door slightly open, not wide open, not comfortably open, but open enough to justify continued investigation. This distinction separates wormholes from many impossible ideas. For example, perpetual motion machines violate fundamental physical principles. Physicists can confidently reject them. Traversable wormholes occupy a different category. The obstacles are enormous. The challenges are extraordinary. Yet no universal law has completely eliminated the possibility. As a result, the discussion continues. Another challenge emerges when we consider what happens as a traveler actually enters a wormhole. Let's assume, just for argument's sake, that a stable wormhole exists. Let's assume collapse has somehow been prevented. Let's assume the structure remains open. What would the journey feel like? Interestingly, many popular depictions probably exaggerate the experience. Films often portray wormhole travel as a violent roller coaster. Lights flash, space twists dramatically, everything shakes, people scream, computers malfunction. The soundtrack becomes very enthusiastic. Reality might be much less theatrical. If a traversable wormhole were sufficiently large and stable, the traveler could potentially pass through quite smoothly. From their perspective, they would simply move through a region of unusual space-time geometry. The strange part would not necessarily be the journey. The strange part would be the outcome. One moment you're here, the next moment you're somewhere impossibly distant. The distance crossed would vastly exceed the distance traveled locally. That's the essential trick. The traveler doesn't race across the galaxy. The traveler follows a shortcut through space-time. The geometry does the work. This idea remains difficult for human intuition. We're accustomed to connecting distance with travel time. Long distances require long journeys. Short distances require short journeys. Wormholes break that relationship. A journey lasting minutes could connect locations separated by thousands of light years. The geometry changes the rules. Of course, additional dangers remain. Even if collapse could be prevented, other problems might appear. Radiation could accumulate. Gravitational forces could become extreme. Quantum effects might destabilize the structure. Nature often introduces complications just when things begin looking promising. Physicists continue debating many of these questions today. The answers remain uncertain. Yet one thing has become increasingly clear. A usable wormhole would require conditions unlike anything humans currently know how to create. The engineering challenge would dwarf every technological achievement in history. Building pyramids would seem simple by comparison. Constructing modern cities would seem simple. Landing on the moon would seem simple. A traversable wormhole would involve manipulating space-time itself. The scale of the task is almost beyond imagination. Still, it's worth remembering that scientific understanding often begins long before technological capability. Humanity understood flight mathematically before building practical airplanes. Electricity was studied long before modern power grids existed. Atomic theory preceded nuclear technology by many years. Understanding comes first. Application follows later, if it follows at all. Wormholes currently reside in that first stage. Physicists are trying to determine what the universe allows. Only afterward can anyone worry about implementation, and that's precisely why the collapse problem remains so important. Every discussion eventually returns to the same obstacle. How do you stop the wormhole from closing? How do you keep the throat open? How do you resist gravity's relentless attempt to eliminate the shortcut? By this point in our journey, wormholes may sound almost plausible. Not easy, not practical, certainly not something we're likely to commute through on a Monday morning, but perhaps possible. Einstein's equations seem willing to permit them. The geometry appears capable of forming them. The idea itself refuses to disappear. And yet one stubborn problem continues standing in the way. The wormhole keeps collapsing. Every time physicists try to create a shortcut through space-time using ordinary matter and ordinary gravity, the same thing happens. The tunnel pinches shut. The throat narrows. The passage disappears. Nature seems determined to slam the door closed. What would it take to keep the door open? The answer turned out to be so strange that many physicists initially found it difficult to believe. Because according to the mathematics, holding a wormhole open might require a form of matter unlike anything humans encounter in everyday life. Not unusual matter, not rare matter, something far stranger, something that behaves in ways that seem almost backwards. To understand why, let's begin with something familiar. Imagine placing a heavy object on a mattress, perhaps a bowling ball. The mattress sinks. The surface curves inward. Now imagine placing a second bowling ball nearby. The two depressions influence one another. The balls roll together. This simple picture is often used to illustrate gravity. Mass creates curvature. Curvature influences motion. Objects naturally move toward one another. Gravity attracts. That attraction is one of the most reliable features of the universe. Planets attract moons. Stars attract planets. Galaxies attract stars. Everything with mass participates. Gravity is always pulling inward, and that's exactly why wormholes have such a difficult time remaining open. Imagine trying to hold open a tunnel while invisible hands squeeze it from every direction. The harder those hands push, the stronger your supports must become. Ordinary matter doesn't help much. Ordinary matter possesses positive energy, positive mass, positive density, all the familiar ingredients that make up planets, stars, people, coffee cups, and the occasional misplaced television remote. Unfortunately, positive energy tends to strengthen the very gravitational effects that cause collapse. Instead of solving the problem, ordinary matter often makes it worse. It's a bit like trying to stop a sinking boat by adding more water. The approach moves in the wrong direction. Physicists gradually realized that something fundamentally different might be required. Not more attraction, the opposite of attraction. Something capable of pushing outward, something capable of resisting the inward squeeze, something capable of supporting the wormhole throat against collapse. And this is where things begin becoming wonderfully strange. In theoretical physics, researchers often talk about energy conditions. These are mathematical assumptions about how matter and energy normally behave. For example, ordinary matter generally has positive energy density. That sounds technical, but the idea is simple. If you examine a region of space containing matter, you expect to find positive amounts of energy, not negative amounts, positive. That's how everyday reality works. Your body contains positive energy. The Earth contains positive energy. The Sun contains positive energy. The universe seems remarkably committed to keeping the numbers on the positive side. Yet when scientists calculated the requirements for a traversable wormhole, they encountered a surprise. The equation suggested that ordinary positive energy wouldn't be enough. Instead, the wormhole appeared to require negative energy density. Negative energy. Even saying the phrase feels unusual. Our intuition immediately begins protesting. How can energy be negative? How can less than nothing exist? How does that even make sense? For many years, physicists asked exactly those questions. The concept seemed deeply suspicious, yet something remarkable happened. Quantum physics began suggesting that negative energy might not be entirely impossible. Before we explore that idea, let's clarify something important. Negative energy does not mean anti-energy. It does not mean reverse energy. It does not mean energy wearing a fake mustache and pretending to be something else. Instead, it refers to situations where the energy in a region becomes lower than what would normally be considered empty space. That distinction turns out to matter enormously because according to quantum mechanics, empty space is not actually empty. This is one of those statements that initially sounds like wordplay. Surely empty space is empty. That's what the word means. Yet quantum physics has spent more than a century demonstrating that reality doesn't care very much about everyday definitions. The vacuum of space is surprisingly active even in regions completely devoid of matter. Quantum fields remain present. Tiny fluctuations occur constantly. Particles appear and disappear. Energy levels shift. The vacuum behaves less like emptiness and more like a restless ocean. Most of these effects remain invisible in everyday life. They occur on scales far smaller than human perception. Yet their existence has been confirmed repeatedly through experiments. Space itself is alive with activity. And within that activity, physicists discovered something fascinating. Under certain circumstances, quantum effects can produce regions where energy becomes effectively negative. Not dramatically negative, not enough to power a spaceship, but negative nonetheless. One of the most famous examples is something called the Casimir effect. The name comes from Dutch physicist Hendrik Casimir, who proposed it in 1948. The setup is surprisingly simple. Imagine two perfectly conducting metal plates placed extremely close together, not centimeters apart, not millimeters, much closer, at tiny scales. According to quantum theory, the space between the plates behaves differently from the surrounding space. Certain fluctuations become restricted. The energy between the plates becomes slightly lower than the energy outside. The result is a measurable force pushing the plates together. Experiments have confirmed this effect repeatedly. The Casimir effect is real. And perhaps most importantly for our story, it demonstrates that negative energy densities can occur, not in science fiction, not in speculation, in actual physics. This discovery electrified theoretical discussions about wormholes. Suddenly, the idea of negative energy no longer seemed completely impossible. Nature already appeared capable of producing it. The next question was obvious. Could enough negative energy be generated to support a wormhole? Unfortunately, this is where the situation becomes challenging again. Very challenging. The amounts of negative energy observed through quantum effects are extraordinarily small, tiny, microscopic, almost unimaginably weak compared to what a large wormhole would require. It's a bit like discovering a cup of water when what you need is an ocean. The basic ingredient exists, the quantity falls dramatically short. Still, the discovery mattered because science often progresses by identifying possibilities before solving practical problems. The first airplanes were fragile and limited. The first computers filled rooms. The first rockets seemed primitive by modern standards. Demonstrating possibility comes before scaling capability. Wormhole researchers suddenly had evidence that the universe allowed at least some forms of negative energy. The door remained slightly open. As investigations continued, scientists began referring to the required material as exotic matter. This term has become extremely popular. You'll encounter it frequently in books, documentaries, and discussions of advanced physics. The phrase sounds mysterious, perhaps even a little dramatic, yet it serves a useful purpose. Exotic matter simply refers to matter possessing unusual properties not found in ordinary substances. Properties capable of violating the energy conditions normally obeyed by conventional matter. In practical terms, exotic matter acts differently, very differently. Ordinary matter attracts. Exotic matter could potentially repel. Ordinary matter contributes to collapse. Exotic matter might resist collapse. Ordinary matter closes the tunnel. Exotic matter might hold it open, at least mathematically. Whether such matter exists in useful quantities remains unknown, and that uncertainty sits at the center of modern wormhole research. Some physicists remain cautiously optimistic. Others remain skeptical. What's particularly fascinating is that exotic matter doesn't merely appear in wormhole discussions. It emerges elsewhere in theoretical physics as well. Whenever researchers explore extreme situations, unusual forms of energy often appear. Black holes, quantum fields, early universe cosmology. Again and again, reality seems willing to entertain possibilities stranger than our intuition expects. This doesn't mean every strange idea becomes real. Far from it. The universe is selective. Many theoretical possibilities never materialize. Yet history has repeatedly demonstrated that unusual concepts deserve careful examination. Black holes once seemed absurd. Now they're routinely observed. Gravitational waves once seemed almost impossible to detect. Now observatories measure them directly. Quantum entanglement once troubled Einstein himself. Today it forms the foundation of emerging technologies. Science has developed a habit of turning yesterday's impossibilities into today's research fields. Whether wormholes will follow that path remains uncertain, but the lesson encourages humility. Nature has surprised us before. It may do so again. Another intriguing question involves stability. Suppose exotic matter exists. Suppose negative energy can be produced. Suppose a wormhole remains open. Would it stay open indefinitely? Not necessarily. Many calculations suggest that maintaining stability could be extraordinarily delicate. Tiny disturbances might trigger collapse. Passing particles might influence the geometry. Radiation could accumulate. Quantum fluctuations might create complications. A traversable wormhole could require constant maintenance. The structure might behave less like a permanent tunnel and more like a balancing act. Imagine trying to keep a pencil standing upright on its tip. Possible in principle, difficult in practice. A wormhole might demand similar precision, yet even those challenges fail to eliminate the idea entirely. Again and again, physicists encounter obstacles. Again and again, the possibility survives, not comfortably, not easily, but stubbornly. The mathematics continues allowing narrow paths forward. That persistence explains why wormholes remain such an active area of theoretical investigation. The concept refuses to die. Every apparent dead end reveals another question. Every obstacle reveals another avenue of exploration. And perhaps most intriguingly, some modern theories suggest that wormholes may be connected to an even deeper mystery. Not transportation, not shortcuts, not interstellar travel, something more fundamental, the very structure of space-time itself. Because in recent years, physicists have begun uncovering surprising links between wormholes and one of the strangest phenomena in quantum mechanics, a phenomenon so bizarre that Einstein famously described it as spooky. And that connection may eventually reveal that wormholes are not merely tunnels through the universe. They may be clues about how the universe itself is built. But before we venture into those ideas, it helps to step back and imagine something simpler. If a wormhole truly existed, and if it somehow remained open, what would it actually look like? What would a traveler see while approaching it? What would the sky look like nearby? And perhaps most importantly, what would it feel like to stand before a doorway connecting distant regions of space-time itself? Imagine that humanity succeeds. After centuries of speculation, decades of calculations, and countless scientific debates, a real wormhole is finally discovered. Not a theory, not a simulation, not a mathematical possibility, an actual wormhole. Somewhere in space, astronomers find unmistakable evidence that a tunnel through space-time exists. Naturally, the first questions would concern safety. The second questions would concern travel. The third questions would probably concern funding. But eventually another question would emerge, a surprisingly simple one. What does it look like? After all, most objects in the universe are reasonably familiar. A planet looks like a planet. A star looks like a star. A galaxy looks like a galaxy. Even black holes, despite their exotic nature, produce recognizable visual signatures. Wormholes are different. Most people have never encountered anything remotely similar in everyday life. There is no natural Earth-based comparison. No cave resembles one. No tunnel resembles one. No doorway resembles one. A wormhole belongs to an entirely different category of object. And because of that, visualizing one turns out to be surprisingly difficult. Popular culture has certainly tried. Films often portray wormholes as glowing tunnels filled with swirling lights. Television shows frequently depict colorful vortexes spinning dramatically through space. Science fiction artists love creating elaborate visual effects. Some are beautiful, some are imaginative. Most are probably wrong, not because the artists lack creativity, because reality appears even stranger. The challenge begins with understanding what a wormhole actually is. A wormhole is not simply a hole floating in space. That description sounds reasonable at first. Unfortunately, it creates misleading mental images. When most people hear the word hole, they imagine an absence of material. A hole in a wall, a hole in the ground, a hole in a piece of paper. Wormholes are different. They are geometric structures within space-time itself. The opening is not merely an empty gap, it is an entrance to a shortcut through the geometry of reality, and that distinction changes everything about how the object would appear. Imagine approaching a wormhole from a distance. At first, you might not even recognize what you're seeing. Light behaves unusually around extreme gravitational structures. As a result, the appearance of a wormhole would likely be dominated by distortions. Stars behind it would appear warped. Their positions would seem shifted. Light would bend around the opening. The surrounding sky might appear twisted and rearranged. In some respects, the wormhole could resemble a gravitational lens. Gravitational lensing is a real phenomenon observed throughout the universe. Einstein predicted it through general relativity. Massive objects bend light. As light passes near a galaxy or black hole, its path curves. Astronomers routinely observe this effect. Sometimes distant galaxies appear stretched into arcs. Sometimes multiple images of the same object become visible. Sometimes rings of light form around massive structures. The universe effectively turns gravity into a giant optical system. A wormhole would likely produce similar effects, but far more dramatic ones. The reason is simple. Light wouldn't merely bend around the wormhole. Some light might travel through it. Imagine looking toward the entrance. Instead of seeing ordinary darkness, you might see another region of the universe. Literally, not a picture, not a reflection, an actual view into another location, perhaps another star system, perhaps another part of the galaxy, perhaps somewhere unimaginably distant. The opening would function less like a hole and more like a window showing somewhere else entirely. Pause for a moment and consider how strange that would feel. You're floating in space. Ahead hangs a circular opening. Inside that opening, you see stars. Nothing unusual there. The universe contains countless stars. Then someone explains that those stars are not located behind the wormhole. They are visible through it. The light reaching your eyes has traveled from a completely different region of space-time. You're effectively looking elsewhere without moving. That possibility alone is astonishing. Several physicists have used advanced computer simulations to explore what wormholes might actually look like. These simulations often produce images that differ dramatically from science fiction expectations. Rather than glowing tunnels, many wormholes appear as distorted spherical regions surrounded by warped starlight. The sky bends around them, background objects stretch and shift. Light follows unusual paths. The resulting view can be difficult for the human brain to interpret because we have no everyday experience with such geometries. One of the most famous examples appeared during the production of the movie Interstellar. The filmmakers worked closely with Kip Thorne, one of the world's leading experts on relativity. Rather than inventing a wormhole appearance purely for artistic reasons, they attempted to calculate how one might genuinely look according to physics. The results surprised even the researchers. The visual distortions proved far more subtle and far more complex than expected. Light wrapped around the structure. Stars appeared duplicated. The geometry created effects that felt almost impossible to interpret intuitively. In a sense, the wormhole looked less like a tunnel and more like a piece of the universe behaving incorrectly. Not incorrectly according to physics, incorrectly according to human expectations. And that's an important theme in relativity. Reality repeatedly turns out to be stranger than intuition. Now let's suppose the wormhole is stable. Suppose exotic matter somehow prevents collapse. Suppose a spacecraft approaches the entrance. What happens next? The answer depends on the specific wormhole geometry. Different theoretical models predict different experiences, yet many share certain common features. One possibility is that crossing the entrance might feel surprisingly ordinary. That's a strange statement, but it's worth exploring. Imagine driving through a tunnel. The tunnel itself may not feel extraordinary. What matters is where you emerge. Similarly, a sufficiently large and stable wormhole might allow a traveler to pass through without experiencing dramatic forces. The geometry does the work. The traveler simply follows the path. From the traveler's perspective, the most remarkable event might occur afterward. One moment they're near one star. Moments later, they're near another. The transition could happen without any sensation of extraordinary speed. Because the traveler isn't outrunning light, they're taking a shortcut. The route itself changes. Still, the interior of a wormhole might not appear completely ordinary. Light entering from both ends would interact. Images from distant locations could become visible simultaneously. The visual environment might seem profoundly confusing. Imagine standing inside a tunnel where every direction shows different regions of the universe. Forward might reveal one star system. Behind might reveal another. The surrounding geometry could create multiple images of the same object. Light paths could intersect in unusual ways. The result might feel almost dreamlike, not because physics becomes magical, because human perception evolved for ordinary environments. We are accustomed to straightforward geometries, rooms, roads, fields, forests, not shortcuts through space-time. A wormhole interior could present visual information unlike anything our brains evolved to process. Researchers sometimes compare the challenge to explaining color to someone who has never experienced sight. The concepts become difficult because no familiar reference exists. Another fascinating question involves distance itself. How long would the tunnel appear? The answer turns out to be surprisingly complicated. From the outside, the two ends might be separated by thousands of light years. Inside the wormhole, however, the path could be remarkably short. This creates one of the most counterintuitive aspects of wormhole physics. Different observers might describe the geometry differently. The universe begins behaving in ways that challenge common assumptions about separation. Imagine a road connecting two cities. The road is 10 kilometers long, everyone agrees. Now imagine a wormhole. One observer measures enormous external separation. Another measures a short internal route. Both descriptions can be correct simultaneously. That's the power of geometry. Distance depends on the path being considered. This realization often surprises people because it conflicts with everyday experience. Yet relativity repeatedly demonstrates that geometry matters more than intuition, more than appearances, more than common sense. The universe follows geometry, we merely adapt. Of course, visual appearance is only part of the story. Travelers would also experience gravity, and gravity near wormholes could become quite unusual. If the gravitational forces vary too rapidly, dangerous tidal effects might occur. These are the same forces associated with black holes. Different parts of an object experience different gravitational pulls. The result can be stretching and distortion. Physicists sometimes refer to an extreme version of this process as spaghettification, not a particularly elegant scientific term, but certainly a memorable one. A practical traversable wormhole would need to minimize such effects. Otherwise, travelers might arrive in a condition unsuitable for sightseeing. This requirement places additional constraints on wormhole design. The structure must remain open, the geometry must remain stable, the gravitational environment must remain survivable. Nature rarely makes things easy, yet the possibility remains, and that's what keeps the subject alive within theoretical physics. Even after decades of research, no fundamental law has completely ruled out traversable wormholes. The challenges are immense, the uncertainties are numerous, the obstacles are intimidating, but possibility survives. What's especially intriguing is that visualizing wormholes often changes how people think about space itself. Most of us imagine space as emptiness, a giant void separating objects. Wormholes encourage a different perspective. They suggest that space-time possesses structure, hidden complexity, unexpected connections. The universe becomes less like an empty container and more like an intricate geometric system. That shift in perspective may ultimately be one of the most important contributions wormhole researchers have made. Even if wormholes never exist physically, studying them teaches us something profound about the nature of reality. Geometry matters. Space-time matters. The shape of the universe matters. And as physicists continued investigating these extraordinary structures, another surprising possibility emerged. Not only might wormholes connect distant locations, under the right circumstances, they might connect different moments in time, which is where the story becomes even stranger. Because once scientists realized that wormholes could potentially link regions of space-time, an unavoidable question appeared. If the tunnel connects space and time together, could it also become a machine for traveling into the past or future? For most of this journey, wormholes have been strange enough. We've explored tunnels through space-time. We've discussed shortcuts connecting distant regions of the universe. We've encountered exotic matter, negative energy, and geometries that seem determined to challenge common sense. Yet, remarkably, one of the strangest consequences of wormholes has barely been mentioned: time travel. The phrase alone tends to change the mood of a conversation. Mention wormholes and people become curious. Mention time travel and suddenly everyone has an opinion. Some become excited. Some become skeptical. Some immediately begin discussing famous movies. And a surprising number of people start wondering whether they should go back and buy certain stocks. The fascination is understandable. Time travel may be the single most persistent idea in science fiction. For generations, writers have imagined journeys into the past and future. Entire libraries are filled with stories built around the concept. Yet, unlike many fictional ideas, time travel occupies an unusual position in physics. Scientists do not dismiss it automatically. In fact, certain interpretations of general relativity seem willing to entertain it. That doesn't mean time travel is possible. It doesn't mean anyone has done it. It certainly doesn't mean someone from the year 3000 is secretly watching this video while pretending to be an ordinary tourist. What it means is something more subtle. The mathematics of space-time occasionally produces situations where the distinction between past and future becomes surprisingly complicated, and wormholes play a central role in many of those discussions. To understand why, let's begin with something familiar. Imagine two identical clocks. One remains on Earth. The other boards a spacecraft traveling at extremely high speed. According to Einstein's theory of relativity, the moving clock runs more slowly. This isn't speculation. It's been tested repeatedly. Atomic clocks flown aboard aircraft behave exactly as relativity predicts. GPS satellites require constant corrections because time flows differently for them than it does on Earth's surface. Relativity is not merely theoretical, it's part of everyday technology. The important point is this: time is flexible. That statement would have shocked many earlier scientists. For centuries, time seemed absolute. Everyone shared the same clock. Everyone experienced the same universal flow. Einstein revealed that reality works differently. Time can stretch, time can slow, time can speed up relative to different observers. Once that realization entered physics, entirely new possibilities emerged. Suppose a wormhole exists. Suppose the two mouths of the wormhole initially sit next to each other. A tunnel connects them. Travel between them is nearly instantaneous. So far, nothing unusual. Now imagine moving one mouth of the wormhole. Perhaps it's placed aboard a spacecraft. Perhaps it travels at enormous speed before returning. During that journey, relativistic effects occur. Time passes differently for the moving mouth. The clock attached to it becomes out of sync with the clock attached to the stationary mouth. This is where things become very strange. The wormhole itself continues connecting the two mouths, yet the mouths now occupy different temporal situations. One has aged less, one has aged more. The result resembles a time difference built directly into the tunnel. A traveler entering one end could potentially emerge at a different time than expected, not because they moved extraordinarily fast, because the geometry of space-time itself has become complicated. Physicists examining such scenarios realize something unsettling. Under certain conditions, a wormhole might function not merely as a shortcut through space, it might become a shortcut through time. The implications are difficult to overstate. Traveling to another star is one thing. Traveling to yesterday is something else entirely. And once the possibility appears, another problem arrives almost immediately: paradoxes. Human beings are remarkably good at creating paradoxes. Whenever time travel enters the discussion, give someone 5 minutes to think about traveling into the past, and they will usually invent a contradiction, sometimes several contradictions. The most famous example is the grandfather paradox. You've probably encountered it before. Imagine traveling backward in time. While visiting the past, you somehow prevent your grandfather from meeting your grandmother. As a result, one of your parents is never born. Consequently, you were never born, which creates a problem. If you were never born, who traveled into the past? And if nobody traveled into the past, then your grandfather meets your grandmother normally, which means you're born, which means you can travel into the past, which means you prevent their meeting, which means you are never born. And around we go. The logic loops endlessly. The paradox doesn't seem to possess a satisfying resolution, at least not an obvious one. For many people, paradoxes like this prove that backward time travel must be impossible. The argument feels reasonable. Reality should not allow contradictions. The universe cannot simultaneously permit and forbid your existence. Something must give. Yet physicists, being physicists, did not stop there. Instead, they began exploring possible solutions. One proposal is known as the Novikov self-consistency principle. The name sounds intimidating. The basic idea is surprisingly simple. According to this principle, events within a time loop must remain consistent. Somehow events conspire against you. Your car breaks down. You miss the opportunity. You accidentally introduce them instead. The universe preserves consistency. No paradox emerges because paradoxical outcomes never occur. At first glance, this sounds almost magical. Yet mathematically, it solves many problems. The timeline remains intact. Cause and effect remain intact. History stays coherent. The price is that free choice becomes limited. The universe effectively refuses to permit contradictions. Another approach is even stranger. This solution emerges from certain interpretations of quantum mechanics. Instead of preserving a single timeline, reality splits. Every possible outcome generates a new branch. When you travel into the past and change something, you don't alter your original history. You create a different history, a new branch, a new universe. In one timeline, your grandparents meet. In another, they don't. No contradiction appears because the events occur in different branches of reality. The logic remains consistent. The consequences become astonishing. Under this interpretation, time travel resembles inter-universe travel as much as travel through time. You're not revising your own past. You're entering a different version of history. Needless to say, proving such ideas remains challenging, very challenging. At present, these solutions remain theoretical, interesting, elegant, unverified. Yet they demonstrate how seriously physicists have considered the problem. Time travel discussions are not merely science fiction entertainment. They arise naturally from attempts to understand space-time. Another famous paradox involves information itself. Imagine receiving a blueprint for a time machine from your future self. You use the blueprint to build the machine. Years later, you travel into the past and hand the blueprint to your younger self. Where did the blueprint originate? Nobody created it. It exists within a loop. The information has no beginning. Physicists sometimes call this a bootstrap paradox. Like the grandfather paradox, it challenges ordinary assumptions about cause and effect. We expect things to have origins. We expect information to come from somewhere. Time loops complicate those expectations. Questions that seem straightforward suddenly become difficult. And that may be the most important lesson of all. time itself appears far stranger than intuition suggests. Even without wormholes, relativity transformed our understanding of temporal reality. Time slows at high speeds. Time slows near massive objects. Observers disagree about simultaneity. The universe already behaves in ways that would have seemed impossible before Einstein. Wormholes simply push those ideas further, much further. They force us to confront questions that everyday experience never prepares us for. Can effects precede causes? Can information exist without origin? Can the past be visited? Can history be changed? Or is history fixed? Physicists continue debating these issues today, and remarkably, some of the most respected scientists in the world occupy different positions. That disagreement tells us something important. The questions remain unresolved. Nature has not yet revealed the answer. One reason for this uncertainty is that wormholes themselves remain hypothetical. No confirmed wormhole has ever been observed. No traveler has emerged from one. No experiment has demonstrated a functioning time machine. The discussion remains theoretical because the objects themselves remain theoretical. Yet theory matters. Theoretical investigations often reveal deep truths even when the objects involved never materialize. By studying wormholes, physicists learn about causality. They learn about space-time. They learn about the limits of relativity. The journey itself produces knowledge even if the destination remains uncertain. Interestingly, some researchers suspect that the universe may possess built-in protections against time travel. Theoretical physicist Stephen Hawking proposed something he jokingly called the chronology protection conjecture. The name sounds almost bureaucratic. The idea is simple. Perhaps the laws of physics prevent time travel before paradoxes can occur. Maybe wormholes become unstable. Maybe quantum effects intervene. Maybe nature simply refuses to permit causality violations. Hawking famously joked that the absence of tourists from the future supported his position. If time travel becomes commonplace someday, where is everybody? Why aren't future visitors constantly appearing? The argument isn't definitive, of course. There are countless possible explanations. Future travelers might be prohibited from interacting with the past. Time travel might only work after its invention. Or perhaps it really is impossible. The mystery remains. What's particularly fascinating is how wormholes transformed the time travel conversation. Before relativity, time travel often belonged entirely to fiction. After relativity, the discussion became scientific, not settled science, not proven science, possible science. And that distinction changed everything. Researchers could now explore the idea using equations rather than imagination alone. The results remain controversial, yet they remain serious. As our understanding of space-time deepened, wormholes evolved from hypothetical shortcuts into potential laboratories for studying some of the deepest questions in physics. Questions about time, questions about causality, questions about reality itself. Still, all of these possibilities depend on one crucial assumption: that wormholes actually exist. And so far, despite decades of searching, nobody has found one. Not in our solar system, not in distant galaxies, not anywhere. If wormholes are real, how would we recognize one? And have astronomers perhaps already seen clues without realizing it? Somewhere right now, an astronomer is probably looking at a wormhole. At least that's a possibility. A small possibility. A speculative possibility. But a possibility nonetheless. The challenge is that if wormholes exist, they may not come with convenient labels floating beside them. No sign saying wormhole this way, no blinking arrow, no helpful cosmic information desk. Instead, a wormhole would likely appear disguised as something else, and that creates one of the most fascinating detective stories in modern astronomy. Because for all the attention wormholes receive in documentaries, books, and theoretical physics papers, there remains a remarkably simple fact. Nobody has ever confirmed the existence of one. Not a single wormhole has been observed with certainty. Not one has been photographed. Not one has been visited. Not one has been measured directly. After decades of research, wormholes remain hypothetical, possible according to certain interpretations of physics, unconfirmed according to observation. That distinction matters enormously. Science ultimately depends on evidence. Mathematics can suggest possibilities. Theories can predict possibilities, but observations determine reality. Black holes provide an excellent example. For many years, black holes occupied a position somewhat similar to modern wormholes. Einstein's equations allowed them, physicists studied them, researchers debated them, yet direct evidence remained limited. Then observations began accumulating. Stars moved around invisible massive objects. X-rays appeared from extreme environments. Gravitational waves revealed black hole collisions. Eventually, astronomers even captured images of black hole shadows. The evidence became overwhelming. Black holes moved from theoretical possibility to established reality. Wormholes have not yet completed that journey. They remain stuck at an earlier stage. Interesting, mathematically respectable, potentially important, yet observationally elusive. And that raises a natural question. If wormholes exist, why haven't we found them? The answer begins with a frustrating reality. Space is large, very large. In fact, much of this entire wormhole discussion exists because space is so large. The universe contains hundreds of billions of galaxies. Each galaxy contains enormous numbers of stars. Many stars host planets. The volume involved is staggering. Searching for rare objects within such an enormous arena is not easy. Imagine being told that somewhere on Earth, a single unusual grain of sand exists. Finding it would be challenging. Now replace Earth with the observable universe. The problem becomes considerably worse. Astronomers therefore face a difficult task. They cannot simply search every corner of space. Instead, they must look for clues, indirect evidence, signatures, effects, patterns suggesting that something unusual may be present. This approach has proven remarkably successful throughout scientific history. Nobody has ever touched a black hole. Nobody has ever held dark matter in their hands. Nobody has ever visited the center of a distant galaxy. Scientists infer the existence of such phenomena through their effects. The same strategy applies to wormholes. Researchers ask a simple question. If a wormhole existed, what would it do? The answer turns out to be surprisingly complicated. One possibility involves gravity. As we've discussed previously, wormholes would alter space-time geometry, and geometry influences the behavior of light. That means wormholes could potentially produce distinctive gravitational lensing effects. Gravitational lensing occurs when massive objects bend light passing nearby. The effect was predicted by Einstein and has since been observed countless times. Entire galaxies can act as cosmic lenses. Galaxy clusters can distort background light. Massive structures reshape the appearance of the universe behind them. Astronomers use these distortions routinely. They've become standard tools of modern astronomy. A wormhole could theoretically produce its own unique lensing signature. Light approaching the wormhole might follow unusual paths. Images could appear distorted in unexpected ways. Background stars might seem duplicated. Certain patterns might emerge that differ from those produced by ordinary objects. The challenge is determining exactly what those patterns would look like. Nature rarely makes things simple. A wormhole doesn't announce itself. It hides among countless other gravitational phenomena. Separating a wormhole signal from ordinary cosmic activity is extremely difficult. Yet researchers continue. Computer simulations have become particularly important in this effort. Physicists create virtual wormholes inside mathematical models and then calculate how they should appear to observers. The simulations generate predictions. Astronomers can then compare those predictions with real observations. Most comparisons yield nothing unusual. Occasionally, however, something interesting appears. Not proof, not confirmation, just interesting anomalies. Astronomy contains many such anomalies. Most eventually receive conventional explanations. A few remain mysterious. One of the more intriguing possibilities involves black holes. At first glance, black holes and wormholes seem very different. One traps everything. The other potentially provides passage. Yet from a distance, they might appear surprisingly similar. Both involve extreme space-time curvature. Both influence surrounding light. Both affect nearby matter. In some situations, distinguishing between them could prove challenging. This possibility has inspired numerous studies. Could some objects currently classified as black holes actually be wormholes? Most physicists remain cautious. Black holes already explain observations remarkably well. Replacing them requires strong evidence. Nevertheless, researchers continue investigating. The question remains open. Imagine observing a distant object. Matter spirals inward. Light bends dramatically. Gravity dominates the environment. The scene looks exactly like a black hole. Yet hidden within that appearance might be something else entirely. A wormhole masquerading as a black hole. A cosmic imposter. An extraordinary possibility concealed behind familiar observations. Again, there is currently no evidence this has happened, but the idea remains scientifically interesting because it suggests a potential path toward discovery. Another promising area involves gravitational waves. These ripples in spacetime were first directly detected in 2015 by the LIGO collaboration. The achievement marked one of the most important scientific breakthroughs of the century. For the first time, humanity could directly observe distortions moving through spacetime itself. The implications were enormous. A completely new branch of astronomy suddenly became available. Researchers immediately began asking what other phenomena might produce gravitational waves. Black hole mergers produced them. Neutron star collisions produced them. Perhaps wormholes could produce them too. If two wormholes interacted, collided, or evolved in certain ways, they might generate distinctive signals. These signals could differ subtly from ordinary black hole events. Future detectors might become sensitive enough to recognize those differences. It's an exciting possibility because gravitational waves provide a completely different method of observation. Instead of studying light, scientists study spacetime itself. The universe reveals information through an entirely new channel. Some researchers have even proposed that certain unusual gravitational wave signals could hint at exotic objects. The evidence remains inconclusive. The search continues. Then there's the possibility that wormholes could influence nearby matter, gas clouds, stars, dust, radiation. Everything interacting with a wormhole would respond to its gravitational environment. Those responses might create observable patterns. Astronomers routinely study such patterns throughout the cosmos. In many cases, the object itself remains invisible. Only its effects are visible. Yet those effects reveal the hidden source. This method has proven incredibly powerful. The planet Neptune was discovered partly because of its gravitational influence on other planets. Dark matter was inferred through gravitational effects. Countless astronomical discoveries began with indirect evidence. Wormholes might eventually follow the same path. A particularly fascinating possibility emerged in recent years through advances in black hole imaging. When the Event Horizon Telescope collaboration produced images of black hole shadows, researchers immediately began comparing those images with wormhole predictions. Could a wormhole shadow look different? Would the surrounding light behave differently? Could future telescopes detect those differences? Studies suggest the answer might be yes. Not always, not dramatically, but potentially. A sufficiently powerful instrument might eventually distinguish between certain black hole models and certain wormhole models. The technology remains limited. The concept remains promising. What's especially interesting is how modern astronomy increasingly relies on multiple forms of evidence. Scientists no longer depend solely on visible light. They observe radio waves, X-rays, gamma rays, neutrinos, gravitational waves. Every new observational tool expands our ability to detect unusual phenomena. A wormhole hidden from one method might become visible through another. The universe often reveals its secrets gradually. New instruments create new opportunities. Yet despite all these efforts, the current situation remains unchanged. No confirmed wormholes, no verified observations, no definitive evidence. This absence sometimes frustrates people. Understandably so. The idea is captivating. The implications are extraordinary. Everyone wants answers. Science unfortunately operates on its own schedule. Evidence arrives when it arrives. Nature reveals what it reveals. Researchers cannot force discoveries into existence. Still, the search itself has value. Even if wormholes ultimately prove non-existent, the investigation teaches us about gravity, space-time, black holes, quantum physics, and the structure of the universe. Knowledge accumulates regardless of the outcome. That's one of the strengths of scientific exploration. Questions remain worthwhile even when answers remain uncertain. In fact, some of the most productive periods in science occur when uncertainty is highest. Mysteries attract attention. Attention drives research. Research produces discoveries. Sometimes the discoveries answer the original question. Sometimes they reveal entirely new questions. Wormholes sit comfortably within that tradition. They're not established reality. they're not pure fantasy. They occupy the intriguing territory between known and unknown, a territory scientists have explored many times before. And while astronomers continue scanning the skies for evidence, another development has emerged from an unexpected direction. Instead of looking outward through telescopes, some physicists have begun looking inward, into the deepest foundations of quantum mechanics. Few phrases in physics sound more intimidating than quantum mechanics. Mention black holes at a dinner table and people usually nod with interest. Mention relativity and someone will probably bring up time dilation. Mention quantum mechanics and the conversation often becomes noticeably quieter. Part of the reason is that quantum physics has earned a reputation, a strange reputation. Even many physicists have admitted that the subject feels deeply counterintuitive. The famous physicist Richard Feynman once remarked that nobody truly understands quantum mechanics. Now, to be fair, physicists understand how to use it extremely well. The equations work, the predictions work. Modern technology depends on it. Computers, lasers, smartphones, and countless other devices exist because quantum theory accurately describes reality. The challenge is not making the theory function. The challenge is developing intuition for it. Reality at very small scales behaves differently from the world we experience every day. Particles act like waves. Waves act like particles. Objects can exist in multiple possible states before measurement. Events occur probabilistically rather than deterministically. And occasionally the universe seems determined to remind us that common sense evolved for survival, not for understanding subatomic reality. For many years, wormholes and quantum mechanics occupied separate territories. Wormholes belonged primarily to general relativity. Quantum mechanics belonged to the microscopic world. One described spacetime, the other described particles. Different theories, different scales, different problems. Yet as physicists dug deeper into both subjects, something unexpected began happening. The two worlds started interacting. And in recent years, that interaction has become one of the most exciting developments in theoretical physics. Because wormholes are no longer viewed merely as speculative shortcuts through space. Some researchers now suspect they may reveal something fundamental about how reality itself is constructed. To appreciate why this idea has generated so much excitement, we need to begin with one of the strangest phenomena ever discovered: quantum entanglement. The name sounds technical. The concept is astonishing. Imagine two particles interacting. Afterward, they become linked in a special way. Their properties remain connected regardless of the distance separating them. Move one particle across a laboratory, the connection remains. Move it across a continent, the connection remains. Move it across the galaxy, the connection remains. At first glance, this sounds impossible. How can two objects remain connected across enormous distances? What exactly is being shared? What mechanism carries the information? Physicists ask these questions for decades. The answers turned out to be subtle. Entanglement does not allow ordinary communication. It does not transmit messages faster than light. It does not function like a hidden telephone line. Yet the connection remains real. Experiments have confirmed it repeatedly. Nature appears genuinely entangled. In fact, quantum entanglement has become one of the most thoroughly tested phenomena in modern physics. The universe seems remarkably committed to it. Even Einstein found the idea unsettling. He famously described entanglement as spooky action at a distance. The phrase has survived for generations because it captures the emotional reaction perfectly. Something about entanglement feels strange, not wrong, not impossible, strange. The phenomenon appears to violate our intuition about separation. Objects that should behave independently remain connected. The universe appears more interconnected than expected. For decades, entanglement remained mysterious. Physicists understood how to calculate it. They could predict its behavior, they could observe its effects, yet deeper questions lingered. Why does entanglement exist? What does it mean? What does it reveal about reality? Then in the early 21st century, an extraordinary idea emerged. Two researchers, Juan Maldacena and Leonard Susskind, proposed a surprising connection. Perhaps wormholes and entanglement are related, not vaguely related, not metaphorically related, fundamentally related. The proposal became known as ER=EPR. The name looks cryptic until you understand the letters. ER refers to Einstein-Rosen bridges, wormholes. EPR refers to a famous entanglement thought experiment developed by Einstein, Podolsky, and Rosen, quantum entanglement. EPR suggests something remarkable. Wormholes and entanglement might represent different descriptions of the same underlying reality. That sentence deserves a moment of reflection. Physicists were proposing that space-time connections and quantum connections could be deeply linked. The implications were profound. For generations, researchers had struggled to unite general relativity and quantum mechanics. The two theories work extraordinarily well, yet they seem fundamentally different. General relativity describes gravity and space-time. Quantum mechanics describes particles and fields. Bringing them together has proven notoriously difficult. EPR hinted at a possible bridge between the two, a conceptual bridge, perhaps even a literal one. To understand the intuition, imagine two entangled particles. Instead of viewing them as separate objects connected mysteriously across space, perhaps they are linked by an extremely tiny wormhole, not a traversable wormhole, not a tunnel large enough for spacecraft, a microscopic geometric connection, a hidden structure woven into reality. This picture remains speculative. No experiment has confirmed it directly, yet it possesses an appealing elegance. Rather than treating entanglement as a mysterious action across distance, it replaces the mystery with geometry. The particles remain connected because they are connected. The relationship becomes physical. The distance becomes less important. And once researchers began exploring this possibility, new questions appeared almost immediately. What if space-time itself emerges from entanglement? This idea may be one of the most radical concepts currently being explored in theoretical physics. For most of history, space seemed fundamental. Space existed. Objects occupied space. The relationship appeared straightforward. Now some physicists are asking whether space might actually be a consequence of deeper quantum connections. In other words, perhaps entanglement comes first. Perhaps geometry emerges afterward. Imagine constructing a city. Most people focus on buildings, yet roads determine how those buildings connect. Remove the roads and the city changes dramatically. Some researchers suspect entanglement may play a similar role. The connections themselves could create the structure we perceive as space-time. Distance might emerge from relationships. Geometry might emerge from information. The universe becomes less like a collection of objects sitting in empty space and more like a network of connections generating space itself. That possibility is difficult to visualize because human intuition evolved within space-time. We naturally assume space comes first. Questioning that assumption feels almost impossible. Yet modern physics has repeatedly challenged assumptions once considered obvious. The Earth feels stationary. It isn't. Time feels absolute. It isn't. Matter feels solid. Mostly, it isn't. Perhaps space itself will eventually join that list. What's particularly fascinating is that wormholes suddenly occupy a new role in this story. Previously, they appeared mainly as transportation devices, interesting shortcuts, exotic tunnels. Now they become something deeper, potential clues about the architecture of reality. The shift is significant. Imagine discovering that roads are not merely ways to travel, they are also clues explaining how cities are constructed. Wormholes may serve a similar function. Even if nobody ever travels through one, understanding them could reveal something fundamental about space-time. Several influential researchers have pursued this line of investigation. Among them is Mark van Raamsdonk, whose work explored how space-time geometry might emerge from quantum entanglement. The central idea is surprisingly simple. Increase entanglement, and regions of space-time become more connected. Reduce entanglement, and those regions become less connected. Push the process far enough, and space-time itself could fragment. The geometry responds to quantum relationships. In this picture, space-time resembles a fabric woven from information, not information in the everyday sense of books and websites. Quantum information, fundamental relationships, connections, patterns. The geometry we observe emerges from deeper structures beneath. Again, none of this has been definitively proven. Theoretical physics remains a frontier. Researchers explore possibilities. Some survive, others do not. The process requires patience, yet the excitement surrounding these ideas is understandable. For decades, physicists searched for ways to connect quantum mechanics and gravity. Now wormholes appear in the middle of the conversation. Not because anyone expected them to, because the mathematics keeps bringing them back again and again. Another intriguing aspect involves black holes. Modern research increasingly suggests that black holes, quantum information, entanglement, and wormholes may all be connected. The relationships remain complicated. Entire careers are devoted to understanding them, yet a broad pattern has emerged. Concepts once considered separate now appear intertwined, like pieces of a puzzle gradually fitting together. The resulting picture remains incomplete. Large sections are still missing, but enough pieces exist to reveal something interesting. The universe may be far more interconnected than we previously imagined. That possibility resonates with a recurring theme throughout this wormhole story: distance. Again and again, wormholes challenge assumptions about separation. At first, they challenged physical separation. Two distant regions might be connected. Now, they challenge conceptual separation. Quantum mechanics and spacetime might be connected. Information and geometry might be connected. Reality itself might be woven together in unexpected ways. It's a remarkable evolution. What began as a speculative shortcut through space has become a potential clue about the foundations of existence. Of course, caution remains essential. Theoretical physics has produced many beautiful ideas. Not all survive experimental scrutiny. Nature ultimately decides. Researchers continue testing, calculating, debating, refining. The story remains unfinished. Yet even if every current wormhole theory eventually proves incomplete, something important has already happened. The concept has expanded. Wormholes are no longer merely about travel. They're about understanding space-time, understanding quantum mechanics, understanding how the universe builds itself. Suppose wormholes really do exist. Suppose they are woven into the structure of reality. Suppose the universe genuinely contains these extraordinary connections. What would that mean for our understanding of existence itself? For thousands of years, human beings have looked at the night sky and quietly assumed something. The stars are far away, very far away. The planets are separated by enormous distances. Galaxies are separated by even larger distances. The universe is vast, and everything inside it occupies its own place. That assumption seems perfectly reasonable. In fact, most of science has been built upon measuring those separations. Astronomers calculate distances between stars. Cosmologists calculate distances between galaxies. Space missions are planned according to distance. Even our language reflects this way of thinking. Near, far, close, distant, separated, connected. We navigate reality through the concept of location, and for good reason. Distance matters. If you want to visit a neighboring city, distance matters. If you want to reach the moon, distance matters. If you want to travel to another star, distance matters even more. The entire challenge of space exploration exists because distance exists. Yet wormholes raise a fascinating possibility. What if distance is not quite as fundamental as it appears? Notice that this question differs from the practical questions we've explored previously. Could wormholes exist? Could they remain open? Could someone travel through one? Those questions are important. Scientists continue investigating them. But now we arrive at a different kind of question. A philosophical question, not philosophical in the sense of abstract speculation disconnected from science. Philosophical in the sense that it asks what the science means. If wormholes are real, what do they tell us about the nature of reality? What do they reveal about the universe itself? Because sometimes the deepest consequences of a scientific idea are not technological, they're conceptual. Consider the Earth orbiting the Sun. At first glance, that discovery simply describes planetary motion. Yet it also changed humanity's understanding of its place in the cosmos. The Earth was no longer the center. Humanity occupied a much more ordinary position. The scientific fact carried philosophical implications. The same thing happened with evolution. The same thing happened with relativity. The same thing happened with quantum mechanics. Scientific discoveries often reshape how we think about existence itself. Wormholes might do the same. Suppose for a moment that somewhere in the universe, a traversable wormhole exists. Not a theoretical possibility, an actual physical structure, a real shortcut connecting distant regions of space-time. What would that imply? One immediate consequence involves separation. Throughout everyday life, separation feels absolute. If two objects occupy different locations, they are separated. If two cities lie hundreds of kilometers apart, they are separated. If two stars lie dozens of light years apart, they are separated. The statement seems obvious, yet wormholes complicate that picture. Two stars might appear distant according to ordinary measurements and still be connected through geometry. The apparent separation remains. The deeper structure becomes more complicated. In a sense, wormholes challenge the assumption that visible distance tells the whole story. This idea appears repeatedly throughout science. Reality often contains hidden layers beneath appearances. A table appears solid. Atoms reveal otherwise. The sun appears to move across the sky. Astronomy reveals otherwise. Time appears universal. Relativity reveals otherwise. Again and again, deeper investigation uncovers additional structure. Wormholes potentially continue that pattern. The universe may be connected in ways not immediately visible. That possibility becomes even more interesting when combined with modern quantum theories. As we discussed earlier, some researchers suspect that space-time itself may emerge from deeper connections, entanglement, information, relationships. In such frameworks, connections become fundamental, geometry becomes secondary, distance emerges rather than existing independently. This represents a dramatic shift in perspective. For centuries, distance seemed primary. Objects occupied locations. Locations determined relationships. Now, some physicists wonder whether relationships determine locations. The difference may sound subtle. The implications are enormous. Imagine looking at a map. Cities appear as separate points. Roads connect them. The map encourages you to think of the cities first and the connections second. Now imagine reversing that picture. Suppose the connections create the cities. Suppose the network comes first. Suddenly, the entire structure appears different. Some modern approaches to physics explore ideas remarkably similar to this, and wormholes frequently appear within those discussions. What's especially fascinating is that wormholes blur categories we normally treat as distinct. Take space and connection. Ordinarily, we think of them as opposites. Space separates, connections unite. Wormholes combine both. The connection exists because of space. The shortcut exists within space. The separation and the connection become aspects of the same geometry. That realization may sound abstract, but it reflects a recurring theme in modern physics. Nature often resists simple categories. Wave or particle. Quantum mechanics says both. Space or time. Relativity says space-time. Connected or separated. Wormholes complicate the distinction. Reality repeatedly turns out to be richer than expected. Another intriguing implication involves exploration. Human history is in many ways the history of overcoming distance. Ancient travelers crossed deserts, sailors crossed oceans, pilots crossed continents, astronauts crossed the boundary between Earth and space. Again and again, humanity reduced effective distance. The world became smaller, not physically smaller, functionally smaller. A journey that once required months eventually required days, then hours, then minutes. Communication followed a similar pattern. Messages once traveled at walking speed. Now information crosses the planet almost instantly. Distance still exists. Its practical significance changes. Wormholes represent the ultimate version of that trend. If they exist, distance could lose some of its authority altogether. A star system thousands of light years away might become more accessible than a nearby region lacking a wormhole connection. Geography itself would change. Maps would change. Civilizations would change. Human thinking would change. The universe would no longer be organized solely by physical separation. Connectivity would matter just as much, perhaps more. Of course, this remains speculative. No evidence currently suggests that traversable wormholes exist, yet philosophical implications often emerge before practical applications. People contemplated the meaning of flight long before airplanes existed. People debated the consequences of space travel long before rockets reached orbit. Exploring implications is part of understanding ideas, even hypothetical ideas. Wormholes also raise interesting questions about individuality and location. Most of us define our position very simply: we are here. Everything else is elsewhere. The distinction feels clear, Yet relativity already complicates such notions. Observers moving differently experience reality differently. Time itself depends on perspective. Wormholes add another layer. Location may depend on geometry. Apparent separation may conceal deeper connections. The universe becomes less straightforward, not less understandable, just more subtle. One reason these ideas capture public imagination is that they resonate with something deeply human. People often feel separated by geography, separated by time, separated by circumstance, separated by experience. The dream of connection appears throughout culture, stories, myths, art, religion, literature. Again and again, humanity explores the tension between separation and connection. Wormholes touch that same theme, not emotionally, physically. They suggest that the universe itself may contain hidden pathways, unexpected links, relationships concealed beneath appearances. Whether those pathways exist remains uncertain. The idea remains compelling. Interestingly, many physicists approach wormholes less as transportation systems and more as conceptual tools. Even if nobody ever travels through one, wormholes help researchers think about spacetime. They illuminate questions, they reveal possibilities, they expose assumptions. Scientific concepts do not need to exist physically to be useful. Imaginary numbers transformed mathematics long before anyone fully understood their significance. Thought experiments shaped relativity. Idealized models continue guiding physics today. Wormholes play a similar role. They challenge intuition, they force deeper thinking, they encourage new perspectives, and sometimes perspective matters as much as discovery. Consider how differently the universe appears compared to a century ago. Before relativity, space and time seemed fixed. Before quantum mechanics, certainty seemed fundamental. Before modern cosmology, the universe appeared smaller and simpler. Each breakthrough expanded understanding. Each revealed hidden complexity. Wormholes belong to that tradition. They remind us that reality may still contain surprises, important surprises, fundamental surprises. One of the most humbling lessons in science is that certainty often ages poorly. Again and again, humanity has mistaken familiarity for understanding. The sky seemed obvious. It wasn't. Matter seemed obvious. It wasn't. Time seemed obvious. It wasn't. Distance may eventually join that list. Perhaps not. Perhaps wormholes will ultimately prove impossible. Perhaps future theories will eliminate them completely. That outcome remains possible. Yet even then, the questions they raise will remain valuable because the questions extend beyond wormholes themselves. What is space? What is connection? What is distance? How is reality organized? These questions survive regardless of the final answer. In fact, they may be the most important part of the entire discussion. The search for wormholes is not merely a search for shortcuts. It is a search for understanding. Understanding of space-time, understanding of geometry, understanding of how the universe constructs itself. And after more than a century of investigation, one fact remains clear. The universe is under no obligation to match our expectations. Again and again, it reveals structures stranger than we anticipated. Wormholes may eventually join that list, or they may remain fascinating possibilities that helped illuminate deeper truths. At present, nobody knows. And perhaps that uncertainty is fitting, because throughout this entire story, wormholes have occupied a unique position. Not established reality, not pure fantasy, something in between. A doorway left slightly open, a question awaiting resolution, a possibility inviting curiosity. After all the mathematics, all the theories, all the speculation, and all the unanswered questions, what conclusion can we honestly reach? Are wormholes genuine features of the universe, or are they beautiful ideas emerging from equations that nature never actually builds? More than a century has passed since Einstein first transformed our understanding of gravity. In that time, humanity has split the atom, walked on the moon, built machines capable of detecting ripples in space-time, photographed the shadows of black holes, mapped galaxies billions of light years away. And throughout all those extraordinary achievements, one question has quietly remained unresolved. Do wormholes actually exist? It's a surprisingly difficult question, not because scientists haven't thought about it, not because the mathematics is lacking, not because interest has faded. The challenge is that wormholes occupy one of the most unusual positions in all of science. They are neither clearly real nor clearly impossible. Most scientific ideas eventually settle into one category or the other. Some are confirmed, others are discarded. The process can take years, sometimes decades. Eventually, evidence accumulates. A verdict emerges. Wormholes have resisted that process. They continue existing in a peculiar middle ground. Mathematics allows them. Observations have not confirmed them. Physics has not eliminated them. Nature remains silent, and so the mystery endures. Looking back over everything we've explored, that silence may be the most important part of the story. Because wormholes were never invented as fantasy. Nobody sat down and designed them for entertainment. Nobody created them to solve a narrative problem. They emerged unexpectedly from serious attempts to understand gravity. Einstein developed general relativity to explain how space-time behaves. The equations came first. The wormholes came later. That fact continues to matter. If wormholes had originated entirely from imagination, scientists could comfortably ignore them. But they didn't. They emerged naturally from respected mathematics. The universe itself appeared to suggest the possibility. Whether the universe actually builds them remains another question. Throughout scientific history, many remarkable discoveries followed a similar pattern. First came the equations, then came the evidence. Black holes provide perhaps the best example. For decades, black holes existed primarily as mathematical solutions. Researchers debated them. Some doubted them. Others defended them. The objects seemed strange, almost too strange. Yet evidence eventually accumulated. Theoretical possibility became observational reality. Today, black holes occupy a central position in astronomy. Could wormholes follow the same path? Perhaps. Nobody knows. The possibility remains open. At the same time, caution is essential. Not every mathematical solution corresponds to something physical. Nature appears remarkably creative, but not infinitely so. Physics permits many possibilities. Reality selects only some of them. The distinction matters enormously. Imagine drawing a blueprint for an extraordinary building. The blueprint may be internally consistent. The design may be mathematically sound. The structure may be possible in principle, yet nobody ever constructs it. The blueprint exists, the building does not. Some physicists suspect wormholes belong in that category, perfectly valid solutions, never realized by nature. Others remain unconvinced. They point out that our understanding remains incomplete. After all, many of the most important questions in physics remain unresolved. Quantum gravity remains unfinished. Dark matter remains mysterious. Dark energy remains mysterious. The earliest moments of the universe remain mysterious. Perhaps wormholes depend on pieces of the puzzle we have not yet discovered. That possibility cannot be dismissed. One of the recurring themes throughout this entire journey has been humility. Again and again, science has revealed realities more surprising than expected. The Earth was not the center of the cosmos. Time was not absolute. Space was not passive. Matter was not solid in the way it appeared. The universe repeatedly challenged assumptions. As a result, many physicists hesitate to make definitive declarations about wormholes. The history of science contains too many surprises, too many overturned certainties, too many lessons about the dangers of excessive confidence. Instead, researchers continue asking questions. Can wormholes form naturally? Can they remain stable? Can exotic matter exist in sufficient quantities? Can quantum effects support traversable structures? Can observations distinguish wormholes from black holes? Every year brings new calculations, new simulations, new theoretical insights. The investigation continues. What's especially fascinating is that wormholes have already succeeded in one important way, regardless of whether they exist physically. They have transformed how scientists think about space-time. A century ago, space seemed relatively straightforward. Today, it appears rich, dynamic, and deeply connected to the fabric of reality. Wormholes helped encourage that shift. By exploring the most extreme possibilities, physicists gain deeper appreciation for space-time itself. Even if no traversable wormhole ever exists, the concept has already proven scientifically valuable. In fact, some of the most exciting developments involving wormholes may have little to do with transportation. The connection between wormholes and quantum entanglement continues attracting enormous interest. Researchers investigating EREPR are not primarily searching for interstellar highways. They're trying to understand reality at its deepest level. How does space-time emerge? How is information encoded? What is the relationship between gravity and quantum mechanics? Wormholes appear repeatedly within those questions. The idea has evolved. It began as a shortcut. It became a bridge. Now it may be a clue about the structure of existence itself. That transformation is remarkable. Many scientific concepts become narrower over time as details accumulate. Wormholes have become broader. The deeper researchers investigate them, the more connections seem to emerge. Black holes, quantum information, space-time geometry, entanglement, cosmology, fundamental physics. The concept keeps appearing again and again. Whether that persistence reflects reality or coincidence remains uncertain, yet it continues drawing attention from some of the world's brightest minds. Another reason wormholes remain compelling is that they sit at the intersection of two powerful human instincts: curiosity and exploration. Human beings have always wanted to know what lies beyond the horizon. Ancient explorers crossed oceans, modern explorers crossed space. The desire remains remarkably consistent. Wormholes represent the ultimate horizon, not merely a route to another continent, not merely a route to another planet, a route that potentially reshapes the meaning of distance itself. Even if the route never exists, the possibility captures imagination. And imagination has always played an important role in scientific progress. Not imagination disconnected from evidence, imagination guided by evidence. Scientists often begin with possibilities, then they test those possibilities against reality. Most fail, some survive. The process gradually reveals truth. Wormholes currently remain within that process, neither confirmed nor rejected, still under examination. Perhaps that uncertainty explains their enduring appeal. Human beings are naturally attracted to unanswered questions. A solved mystery becomes knowledge. An unsolved mystery remains an invitation. Wormholes continue inviting exploration, not because they promise easy answers, because they resist them. The story remains unfinished, and unfinished stories possess a special kind of power. As we approach the end of this discussion, it's worth remembering something important. The universe does not owe us wormholes. It does not owe us shortcuts. It does not owe us convenient routes between stars. The cosmos has never shown much concern for human preferences. Reality is what it is. Our task is discovering it. Sometimes the answers are exciting, sometimes they are disappointing, most often they are surprising. If future observations eventually reveal wormholes, the implications could be extraordinary. Physics would enter a new era. Our understanding of space-time would expand dramatically. Questions once considered purely theoretical would become practical. Entire fields of research would transform. The discovery would rank among the greatest scientific breakthroughs in history. If future observations fail to find them, the story remains valuable. Scientists will still learn something profound. They will better understand the limits of space-time, the limits of gravity, the limits of geometry. Knowledge grows either way. That is one of the strengths of science. Negative results remain informative. Reality reveals itself through both what exists and what does not. At present, the most honest answer remains remarkably simple. We don't know. For some people, that answer feels unsatisfying. For science, it is often the beginning. Every major discovery starts with uncertainty. Every investigation starts with questions. The willingness to admit ignorance is what allows understanding to grow. And wormholes remain one of the greatest unanswered questions in modern physics. Maybe they are real. Maybe they are mathematical curiosities. Maybe they are clues pointing toward deeper theories not yet discovered. Perhaps future generations will look back and wonder why the answer seemed so difficult. Or perhaps the mystery will persist far longer than anyone expects. The universe has surprised us before. It will almost certainly surprise us again. For now, wormholes occupy a unique place in our understanding of reality. They are possible enough to study, uncertain enough to debate, strange enough to fascinate, and profound enough to force us to rethink some of our most basic assumptions about space, time, distance, and connection. Not bad for an idea that began as an unexpected feature hiding inside a set of equations. As the night sky continues stretching overhead and distant stars continue shining across unimaginable gulfs of space, the question remains waiting among them. Somewhere out there, hidden within the geometry of the cosmos, there may be shortcuts we have not yet discovered, or there may be none at all. Either way, the search itself tells us something important. Human beings are curious creatures. We look outward, we ask questions, we challenge assumptions, we investigate mysteries, and sometimes while searching for answers, we discover that the universe is even more remarkable than the question that started the journey. Perhaps that's the real lesson of wormholes. Not that they necessarily exist, not that they necessarily don't, but that reality remains larger, stranger, and more interesting than any generation fully expects. And with that thought in mind, somewhere beyond the theories, beyond the equations, and beyond the limits of our current knowledge, the universe continues keeping a few secrets of its own.